So you guys probably know this, but I'm Henry. I go by Toadstorm on the internet. I have been a visual effects guy in film and commercials for, I don't know, something like 15 years now. And I am the developer of MOPs. That's all I got right now, really. I live in San Jose with a bunch of cats and my wife. Let's get started. So before we go into anything else, I just want to do a quick, boring PowerPoint presentation on sort of conceptually what MOPS is about, and then we'll go into installing it, because I imagine some of you probably had trouble with it, and so I just want to go over the installation process with everybody before we go any further. So let's get to the PowerPoint. I'm going to share my screen, and please let me know if something isn't working. Okay, MOPS 101. So just to get started, MOPS is a free and open source toolkit for motion design and animation in Houdini. It's built to take complex mathematical operations like translations, rotations, pivot adjustments, scaling, things that are honestly mathematically kind of tricky, and abstract them into simple systems that you can animate gesturally with just a couple of keyframes. This should be playing a video, and I really apologize for that. There we go. That core system can be used to create all kinds of complex behaviors from just a few conceptually simple nodes. MOPS also includes several higher level tools to help solve common motion design problems, such as adjusting the timing of instance animations or moving objects along a path, things that most people know how to do in Houdini, but they can be kind of painful to set up. They can also be used to drive any other kind of node in Houdini interchangeably with SOPS, since everything MOPS is doing writes back to common attributes that are used everywhere else in Houdini. And this isn't playing because PowerPoint hates me, but this is one that you've probably seen from Paul Estevez, who also teaches here. The thinking behind most of the higher level tools in MOPS is to enable something that I call gestural animation. So it's using a few simple controls with minimal keyframes to get complex results. So you just have less things that you need to dial in. With traditional methods of animation, if you were trying to animate something like this, you'd be spending all day setting keyframes, and then you would never be able to adjust them. And that's just for the first version. Approaching this procedurally can get you results way quicker, and thankfully Houdini excels at that approach. MOPS it sort of acts as an extra UX layer on top of what Houdini is already doing under the hood. So it takes advantage of the really powerful architecture that Houdini already gives you, and then just makes some of these common motion graphics tasks a little bit more accessible. In the first lesson, we're going to go over the basics of the system, and then we're going to show how some of the more straightforward nodes in MOPS work. Later on, we'll talk about some of the more complex nodes in MOPS that take a little bit more thinking to use, or just like not quite as straightforward to work with. And then in the third lesson, we're going to talk about all the scary math that MOPS relies on, and also all of computer graphics relies on. So a lot of terrifying things like trigonometry and linear algebra. Just real quick before I go into anything else, after this lesson, if you want to learn more about MOPS, like where to look for help offline, there's a few different places where you can get information. The first place is the MOPS wiki, and this is on GitHub, where you would get the rest of where you actually download MOPS. The wiki has notes on every single node within MOPS, and it also has links to example files. So it's a good place to check if you just need an overall survey of what different nodes do, or if you want to go through a basic tutorial to just sort of understand how the system works. There's also a Discord server, which I highly recommend. I'm on Discord all the time, and there's a lot of other people here in different time zones who are pretty experienced with MOPS, who are happy to answer questions. So if you get stuck and you need help fast, it's a really good place to look. MOPS Twitter is usually where I announce updates first. There's also a MOPS Facebook group that I'll link to next, but Twitter is just a little bit easier to post to. So anytime there's a new release or anything new in MOPS world, this is the first place that I'll post it. There's also a forum that isn't as widely used, but the advantage it has over Discord is that everything is logged. So you can search here for answers to common questions, but Discord is probably going to get you answers faster. It's just more trafficked. And now that the boring slideshow is done, we can actually start making cool stuff. Let me just open up my other Houdini. Okay. So the first thing that I want to talk about is sort of, and sorry, if you haven't already downloaded this, if you go to the class link, there is a file that I posted there called 101.zip, and it has all of the files that I'm going to be working with. The first one that I'm looking at right now is called 01 attributes and intrinsics. Oh, you know what? I skipped the installation step. I'm sorry. first time. So what I want to do now is go over the installation process for anybody who's been stuck and then show you how to quickly update, because it's something that you'll be doing often. I tend to update the software pretty regularly. Let me just bring the browser over here. So if you're not already familiar with GitHub, it's not the most accessible place. If you are familiar with GitHub, then I assume that you already know how to like clone a repo, and I'm not going to bore you with the details. But if you need to download MOPs manually, if this is your first time installing it and you don't know how to use Git, the place that you would go, I mean, obviously you go to github.com/toadstorm/mops. And in the corner here, you're going to see a releases page, and the latest release is always going to be right here. If you just click on the releases page, you can see a list of all of the different releases that have gone through. I cycle between stable builds and experimental builds, depending on what kinds of things I'm tweaking. What you'll want to do is on MOPS 1.7.1 stable, you'll go to the source code zip here and just download that. So just put that wherever. Next, what you're going to want to do is pick a location that you want to install MOPS to. And this is kind of arbitrary. It doesn't really matter where you decide to put it, although I'd highly recommend not putting it inside your documents folder where Houdini, the document/Houdini 19.5 in your Houdini home folder. Don't put it there, and don't put it inside a Houdini installation. You'll regret it. What I recommend doing is just picking an arbitrary folder somewhere on your system where your other plugins might live. For me, I put it in projects, VFX, and then I have this MOPS directory. And all you need to do is just extract that zip to this location and then remember where this directory is, because this next part becomes important. The next step beyond this, and again, all of this is documented in the MOPS wiki, but I just want to go over it here first for all of you. I'm on Windows, on OS 10 or Linux. Yeah, the exact directories you use are different. I hope you know what they are, because I can't necessarily tell you on a Windows machine. But what you'll do is open up your documents or preferences directory where the Houdini preferences folder is, right? So on Windows, it's documents/Houdini and then the version that you're using. So I'm on 19. And within that, you may or may not find a packages directory. If you've never used a Houdini package before, you won't see this directory. It doesn't come by default. So you'll have to make it, create a new folder and make sure it's named exactly this, packages. When you boot Houdini, if it finds a packages directory in any of the scanned paths that it's set to look for packages in, and that's dependent on your system environment. But this directory, your Houdini, version number directory, where all of the rest of these preferences are stored, by default, this is the first package directory to be scanned. You can add others if you know how to configure the environment, but I don't want to go into that here. So make the folder if it doesn't exist, and then open it up. In the MOPS installation, you're going to see a mops.json, and the JSON file is the package. In Houdini, it's basically a sort of shortcut way to configure your system environment on Houdini launch so that it's setting keys that say, this is where to scan for OTLs, this is where to scan for Python scripts, this is, and so on. So if you edit this file in a text editor, so just take a second. You're going to see a couple of things. You're going to see MOPS here as an environment key, and then you're going to see a couple other things at the bottom, this like path thing here. This is what actually sets the environment, like path in a Houdini package. This is a little confusing. Sets the Houdini path environment variable, which tells Houdini where to look for tools. So how do I do that? Sorry, I might be able. Oh yeah, there we go. No, I can do it in this one. This is the only thing that you need to change up here. And you just need to set this to be the exact path where you copied MOPS to. So on this, I have it in D projects VFX MOPS. So I would just copy this path, paste it here. And the only thing that you need to make sure of when you do this is if you're on a Windows machine, Windows likes to use backslashes for path instead of forward slashes, and this gets everyone. All you got to do is change these to forward slashes. And this is like a long-running irritation with Windows, but they use backslashes to separate file folders. And backslashes are escape characters in most programming languages. And most of the time when you're writing a text-based parser, it basically looks at those backslashes and thinks that you mean something very, very different. So make sure if you're on Windows, you change these to forward slashes, and then save this JSON file, and then copy it into your packages directory. So I've already got mine here configured, and let me just show you the one that I've already pre-configured. And it's already set to D projects VFX MOPs, that same exact path using forward slashes. Once that's saved and in your Houdini directory, if you boot up Houdini, you should see up at the top here, if you don't see these MOPs shelves, you can go to the tool shelf here, go to your shelf sets. Sorry, not your shelf sets. This plus button right here. Go to shelves, and you should see a MOPs shelf. If you see it, the installation's good. You're ready to go. It is also possible to install MOPs by directly editing the Houdini.env file, but I don't recommend doing that. It's kind of the old school way of doing things, and especially if you're using a build of Houdini 18.5 or later, I think they've solved most of the issues that were happening on packages in previous versions. So stick with packages if you can. It's way easier to deal with. And it also means that if for whatever reason you need to disable MOPs for a certain project, you don't have to go in and start performing surgery on your Houdini env to make that happen. You just move that JSON file somewhere else to disable the package, and you're good to go. The last thing that I want to go over is once you have MOPs installed, let's say you have an older version, because I'm using 1.7.1. I just released it like maybe 2 days ago. If you're using an older version, the only thing that you have to do to update is, again, if you're a big nerd and you know how Git works, you can just use git pull and you're good. Otherwise, if you go to MOPs here, the shelf, and you see this thing with an arrow on it called MOPs Updater, if you click this, it's going to connect to GitHub and automatically give you both the stable and experimental branch. You're going to want to grab the stable branch for this one because 1.7.1 is the most recent release, and it's stable. And then you can select 1.7.1 from the dropdown and then just hit apply update. Once that's done, it's going to think for a second because it has to pull the package from GitHub, unzip it, copy it to where your previous MOPs install was. It's essentially going to overwrite the installation in place, and then restart Houdini, and you should have 1.7.1. Before I continue, does anybody need time to update? Does anyone not have MOPs installed and need help? I just don't want to go into the actual tutorial until we've got all that cleared. You can. I will say that there's some bug fixes that have gone into 1.7.1 that you might notice slightly different behaviors on certain nodes if you don't have the most recent one, but we're only going over pretty basic concepts in this one. So if you see different results in what you're doing from what you're seeing on my screen, it might be because of a version mismatch, but it's not gonna, the overall core concepts of MOPs haven't changed. So you can still follow along. It's just possible you might see different results from me. That's all. Yeah, okay. So that's a Python 2 to Python 3 translation error, which hopefully we're not going to see too often anymore now that Python 2 has been cycled out. If you see that, it means you're going to have to just download and overwrite your existing install manually. Okay. The last thing that you're going to want to download is, if you haven't already gotten it, go to the Houdini.School link for this class and grab the 101.zip file. And then open up the first file, which is called 01 attributes and intrinsics.hip. You don't have to necessarily download this, but it's going to just make it easier because this is just a demo file that's meant to explain how template point attributes and intrinsics are linked. And so there's a bunch of VEX in here that you're not going to want to really type in yourself. So I'm going to bring that instance over here, and we're going to get started. So under the hood, Houdini uses specific attributes to describe where to copy things. And Houdini uses attributes all over the place as a way of being able to customize what's going to happen on any given point or primitive. And most of you guys probably already know that. Template point attributes are special in that both for the copy to point stop and for point instancing and for a lot of other things that involve copying in Houdini, there are specific attributes that the copy to point SOP and the instance object work with that describe where things go in space. And a huge chunk of MOPS is about manipulating the transforms of objects, so like where they are in space. The problem with this system, and it's just sort of it's an evolving thing, so there's always going to be glitches in it, is that template point attributes are one side of this. Like things like p scale, n, up, orient, all of these things that you've probably worked with before when you're trying to figure out how to orient and position copies. But with packed primitives, which are essentially instances, there's a second layer to this, and that layer is intrinsic transforms. So intrinsic attributes are sort of these hidden attributes that you may or may not be too familiar with. And there's a lot of them. They're all over Houdini. And if I can show you right now, if you open up the attributes and intrinsics object here, and the display flag should be on this copy to points. So we just have this simple grid of pig heads here. If you go to the primitives tab and you look at this thing that says intrinsics, you can see I don't have any primitive attributes on any of these. If I open this up, though, there's a bunch of sort of semi-hidden attributes here that Houdini adds for you. You don't have control over really generating these things. They're just there. And they mean a lot of different things. You have bounds, and this describes like the actual min and max bounding boxes of each one of these. You have geometry ID, which is just sort of like where, sort of a hash of where this object came from. You can see they're all the same because they're technically pointing towards the same pig head. And then the important one, at least for what we're doing right here, is the transform intrinsic. And without going into the math yet, this is a matrix that describes the position, orientation, and scale of each copy. Actually, sorry, this is just the orientation and scale. I'll explain the difference later.
These intrinsics are here regardless if it's packed, or is this come when it's packed? Like, do you get the intrinsics only when it's packed? Or
so the transform intrinsic specifically, you only get from packed primitives.
Okay.
But there are a lot of intrinsics in Houdini that mean different things. For example, if I were to just drop down like a line SOP, and then so it's a simple polyline, and then go to the intrinsics tab, you can see that it generates this thing called closed. And this tells me whether this polyline primitive is a closed primitive or not. If I were to make a circle and do the same thing and look at that intrinsic, it says 1 because this is a closed surface. It's actually drawing a fill. If I were to use the end SOP to unroll it, so like I'm going to do unroll with shared points to turn it into a curve, now it's 0. So some of these things Houdini is just doing for you under the hood. A lot of these attributes are read-only. You can only read them in like in your own SOP networks to sort of say, like maybe you're writing an operator that needs to run on closed curves differently than it runs on open curves. You could read this attribute and use that to change the logic of what you're doing under the hood. Some attributes, some of these intrinsics you can write to. It's not consistent which ones you can and can't, but the transform intrinsic is one that you can write to. And this is sort of a central part of what MOPS does, is it tries to unify this template point attribute world with the primitive intrinsic world so that you can kind of use the two interchangeably and modify them after the fact in a way that's a little less painful, because normally intrinsics can only be modified using VEX.
I see. And then why does Houdini hide the intrinsics or make it less obvious for you to find? Just to not overwhelm you?
Yeah, I think that's a good chunk of it, is to just, you wouldn't necessarily want to see a 4x4 transform matrix attribute. So like 16 columns in your spreadsheet on every instance geometry that you've got at all times. It's not necessarily, something that most artists would want to care about. So they kind of tuck it away. And because a lot of these attributes are read-only, that's another big reason why you would want to hide them, is because they would just clog up the spreadsheet otherwise. Okay. So with template point attributes, and hopefully most of you are familiar with these, this is things like orient, ROT, scale, P scale, and P technically is a template point attribute when you're copying to things. They are telling Houdini how to copy things. So I have a grid here that I'm going to instance to. And in this example, what I've done here is I've set up sort of a switch here that, let's set this to 0. And you can see that all the pig heads are the same scale, they're pointing in the same direction, and they're copied to each point of the grid. Go ahead and click on this wrangle here and look at this VEX. I realize it's a lot of it, but what this is describing is sort of what the defaults are. Like, what are the template point attributes in their default state when you're just copying to something? So I have the N attribute set to positive Z, and this is how Houdini understands instances to work. Like, when you're copying something to points, it expects that your object is going to be facing forward towards positive Z, and its up axis, so what determines where the top faces, is positive Y. And this is consistent across Houdini. Like, it's just sort of expecting that that's how your geometry to instance is going to be aligned. Scale is a vector in XYZ, and it just assumes by default that everything is scale 1. And then P scale is sort of a multiplier on top of that. So you can use both simultaneously, and they'll multiply against each other. N and up are how most people like to think about orientation if they're not thinking about it in Euler angles, because it's just conceptually not that hard to see. For example, real quick, if I go to these template points and I use a MOPs visualize frame, this is a way of visualizing orientations on points. And it does not work in Houdini 19 just yet, but if you double click to go inside, you can see the visualizer. And so you can see that every one of these points has Y, the green axis, facing up, and blue, the forward axis, pointing forward. There's also a red axis that's pointing towards the side, which you don't really need to worry about yet. I'll explain more about what this all means in the third part when we start talking about math. But N and up basically means this. You have a forward and an up axis. If I go back to the attribute wrangle here, there are other kinds of attributes that copy to points and instancing in Houdini will work with as well. You have Orient, which is a quaternion. Don't bother trying to understand what that actually means, these numbers. It's crazy, like wizard math that most people, myself included, don't really have an intuitive understanding of because it involves imaginary numbers. The only thing that you should know about this is that 0001 is default, and it just means like the same transform we already looked at. Z is facing forward, Y is facing up. The cool thing about quaternions is that they interpolate very easily and accumulate easily, so you can multiply them together to accumulate rotations. And a lot of computer graphics, especially in game engines, use quaternions under the hood to define orientations because they blend really, really well. You're never going to get gimbal lock or flipping with them. You also have ROT, which is sort of like an extra rotation on top of the orientation. You have transform, which you'll see more often when you're using kin effects. And this is yet another template attribute that you could optionally use, which describes essentially the same thing as the transform intrinsic unpacked primitives. It's a 3x3 matrix that describes orientation and scale and space. And then you have pivot, which just describes an offset in local space for each of these objects from the center of the object. So I know this is a lot, but this is sort of like a brief survey of what all of these things do. If you toggle the switch here and then go to adjust template attributes, what I've done here is built a very quick little thing that allows you to sort of set what these attributes are using channels. So go ahead and put your display flag on copy to points, and then you can kind of play with these values. This is what you would be setting using other Houdini SOPs under the hood, but you can see that it's not very user-friendly. Like, for example, if I drag down scale, that's an obvious one, and I can just sort of set this, and scale is sort of easy to understand. But when you're dealing with things like up, like if I want these things to be facing to the side, if I turn this to 1, like, now they're kind of facing diagonally out. I can try and take this down, but oh no, sorry, this one. And now that I have the up vector facing towards positive X, you can see they're all leaning towards the side. But this is not fun to work with. This is kind of a pain to set these things. And that's why you have tools like in Cinema 4D, you have MoGraph, or in most 3D software, you have sort of an abstracted layer on top of this where you can start talking about things in terms of Euler transforms, rotate 90 degrees on this axis, rotate 90 degrees on this axis, because it's just easier to think that way. But Houdini under the hood wants to see things in these vector attributes. So this, I'm rambling a bit here, but this is important in that Houdini kind of expects you to be setting these attributes in a way that computers like to see and not necessarily the way that you want to see it. So let's jump out of this one. And then just in this other object network here, MOPS setting both. Here, I just want to really quickly go over sort of what MOPS is thinking about under the hood. So again, I've got this pig head, and then I've got a grid here. And let's go to this copy to points. So MOPS transform here is basically, it's very similar to the transform SOP, but instead of working on your entire geometry stream as a single object, it works on each one of those points independently. So for example, if I were to transform this grid, and this is obvious, but if I transform this grid and do, let's say, a 45 degree rotation along Y, the whole thing rotates 45 degrees. MOPS doesn't think that way, at least not by default. What it's going to do instead is nothing. At least when you look at the grid by itself, you're not going to see anything. You can see that the orient attribute has changed if you've got your spreadsheet open. And just as an aside, I recommend having your spreadsheet open all the time. Like never close it. It's the most important thing in Houdini. It's almost more important than the viewport. Like have the spreadsheet open. It will save you so much grief. Just being able to sanity check these numbers when you're trying to troubleshoot things. And let's go down to copy to points here. So now you can see that each of these guys individually is rotated 45 degrees. And this is what MOPS is doing, is it is sort of individually adjusting the template attributes on each one of these points that you're copying to. So I'm going to set this back to 0. And let's just put the display flag on step 1 now. So what MOPS is doing is it's literally setting the orient attribute on these things. And then when you run copy to points, that orient attribute is used to orient each one of the copies that that's generated by the copy to point SOP. You probably already know how that works. Like it's one of the first things you learn when you're dealing with Houdini. But what MOPS also does is, in an attempt to unify the packed transform thing and the template point thing, I can drop another MOPS transform after the fact here, after the copy to point. So I already have template point attributes here. And just as if I were to try to edit like the orient attribute or N or up after these primitives are already copied, it wouldn't do anything because Houdini's like, well, you already made these copies. I'm not changing it again. MOPS will set both. So it's going to modify both the template attributes that you see here, and it's going to modify the transform intrinsics that you see here. So if I go over to the primitive view, and again, I'm going to open up the intrinsics list, and I'm going to turn on transform because this is the one that I care about most for MOPS stuff right now. By default, if everything is facing the default orientation, it's going to look like this. So 1 0 0 0 1 0 0 0 1. And without getting too mathy about this yet, because we're a little early, what this is basically saying is 1 0 0 means X faces X. 0 1 0 means Y faces Y, and 0 0 1 means Z faces Z. So like everything is as it is supposed to be. That aside, go back to this MOPS transform modifier and now try rotating this. And you'll see that each one of these copies, even though we're modifying this after these points have already been copied, what MOPS is doing is setting these intrinsic transforms based on the parameters that we set. So if I rotate 45 degrees, you can see that I get these very different numbers here. And each one of these copies is rotating in turn. What it's also doing at the same time is it still sets these template point attributes at the same time. So it's trying to unify these two things together so that later on, if you need to do another operation to these transforms, or if you need to use these points to maybe swap out the pig heads for something else, you have these attributes ready to go under the hood, and you can just continue to use them along with the rest of Houdini interchangeably. So that's a big part of this, is like MOPS is going to let you, in either one of these settings, you can either go about the traditional copy to points method where you modify your template point attributes, and then at the end of the chain, you copy, and now all of your things are instance, or you can manipulate them earlier, or you can do both. It doesn't matter. Like MOPS will let you do both of these things. So to further drive this home, let's go here to step 2. Now, what I've done here is I've used a MOPS randomize, and I just have randomize orientation set. So all of these things are pointing in random directions. If I click on reset template attributes here, this is active right now. And what this is doing is setting orient, scale, and pivot to be defaults, what they're supposed to be. And you can see that Houdini doesn't care. I've reset orient, but the intrinsic transforms are already set. So setting them manually back with an attribute wrangle is going to do nothing because the points are already copied this operation doesn't modify the intrinsics. But with MOPs, if I go to step 3 here, if I then take that orient attribute, so these attributes are all still live. I have orient, scale, and pivot all set to their defaults. If I use MOPs to basically set these attributes, to take these and apply them to the intrinsics, and that's what apply attributes does, and we'll go into detail on this later, now everything is facing forward. So MOPs, again, there's a lot of different ways that you can use it, but what it's going to do is take those template attributes, the one that you're going to be more used to working with, and the ones that you can set using Houdini or the rest of MOPs, how you can mix and match however you like. MOPs will take those values and apply them back to the intrinsics after the fact. So let's again go to step 4. And so what I'm doing here is I have a MOPs randomize set on these same pig heads. And you can see that they're randomly scaled and they're randomly oriented. Again, just messing things up. These template point attributes that it's setting. So if I click on this, you can see I've got orient and I've got a randomized scale vector on each of these things. Now I'm taking a rubber toy here and just running match size on it to center it, and I'm copying it to the same points as those pig heads. And you can see that they have exactly the same. Let's go do a before after here. Here's the pig heads. Here's the rubber toys. They have the same transforms. So again, I'm just trying as hard as I can to drill the point home that what it's doing is unifying these two approaches. So you have points with template point attributes and you have packed transforms, and you can change them before, after, in the middle, however you want, and then just apply those back to the packed transforms. And MOPs will just sort of take care of it for you under the hood.
So basically, you can apply MOPs, you can change the point attributes at any point downstream, and it will go upstream and tweak the template point attributes to modify them.
It's not technically going upstream, but what it's doing is sort of setting both. So when a packed primitive is already generated, when it's copied, that transform intrinsic is the only thing that matters. That's what tells Houdini how this thing is positioned and oriented in space.
How does it do that after the copy to points? Like you've already set your copy to points and everything is copied, and then afterwards you're able to still manipulate it?
Yes, it does that by setting the transform intrinsics. And that's the annoying part that you would not necessarily want to do as much by hand. If you want to see it, for example, I've got this thing that's like setting the orient attribute here, and it doesn't apply until I run MOPs apply attributes, right? If I go back to this step 2 here and go to this, I can take this orient attribute and use it to reset these transforms. But the way that you have to do it is a little bit ugly. What I'm going to do is say, I'm going to make a 3-dimensional matrix, just call it M, and set it to be, let's see, I'm going to convert this orient attribute into a 3x3 matrix. And then I'm going to say set prim intrinsic. And there are slightly simplified functions that you can do with this too, but I'm using set prim intrinsic under the hood in MOPs. And then I can say, okay, set the transform intrinsic for each point number to be equal to M. And now it's going to lock that in place. But you can imagine that if you have to do this every time you just want to transform stuff after you've copied it, it's going to get really annoying. And right. MOPs is meant to save you from that irritation.
So that's really interesting. So you're allowed to still manipulate it afterwards with the intrinsics. I see.
Yeah. And again, like the intrinsics are sort of semi-hidden from you, and not all of the attributes are easy to understand. And like you have to start dealing with, even dealing with matrices for people who aren't used to them can be it's just not intuitive to work with. Mm-hmm. So you can, and not every intrinsic can be set. The transforms can though. And this is something that comes up a lot when you're trying to manipulate things. Is like there's sort of 2 approaches you can take. One, and what Houdini expects you to do, generally speaking, what they want you to do is set all of these attributes up early in your flow and then copy at the end. Right. Because it just assumes like by the time you get to the copy operation, all your template points are set up and you're good to go. Right. And in a lot of cases that works, but it can still be kind of tricky to set those attributes. If, for example, just doing the classic like 90-degree rotation on one axis on your template points, or like rotating along local axes, like that can be really tricky to do on those points when all you have are things like N and up. And it's, sorry to derail.
No, it's okay.
MOPS is just allowing you to think both ways. So if it's easier for you to think one way and to set all that stuff up in advance, you can do it that way just by using MOPS transform before you get to the copy operation, or you can manipulate them afterwards. It's entirely up to you. And there's like a slight performance difference, but it's not necessarily one is better than the other. It really depends on your network and what nodes in your network are time dependent and what aren't. So like, I can't tell you that one way is necessarily better than the other. It's really just like, how do you prefer to work and exactly how is your network set up? Yeah. The idea is to just allow you to sort of think both ways about it, and also to give you an interface to be able to easily set those attributes so that you don't have to think so hard about how you're rotating them. Okay, so from here on out, because we're not going to be writing nearly as much VEX now, I'm just going to drop all these building blocks with you. So just give me 1 second. Okay, so MOPS is sort of roughly divided into 4 different parts. And real quick, I'm just going to drop down a geometry container and dive inside. So if you open the MOPS, or if you open the tab menu and look at MOPS, it's broken into these 4 parts. You have Falloff, and I'll get to these later, but these are similar to Cinema 4D Falloffs, where it gives you the ability to sort of change how much something is affected by an operation. You have generators, which are actually making geometry, or in some cases modifying geometry, but in a way that is not what you would typically think of as a modifier. It's not like adjusting transforms of things. You have modifiers, which are things that are basically changing the position, orientation, or scale of things in space. And then you have tools, which are a number of sort of miscellaneous things that don't neatly fit into these other categories, or they are low-level API nodes that are sort of the building blocks of MOPS that you can use either for simple operations or to build your own MOPS nodes later out of parts. And we'll go into some more of these later, as there are some useful ones that you'll use all the time, and there's some that are a little bit more esoteric. But what we're going to start with is generators. So how do you make stuff? And so I am just going to call this instancer, because this is going to be the first thing we go into, is the MOPS instancer. The MOPS instancer is sort of like a copy to points SOP, but with a very different interface for how you would wire in inputs and distribute things. And just as a caveat, the instancer was written in Houdini 16.5, and a lot of things have changed about copy to points since then. The way that you can use attributes to describe what object, the variant attribute or the piece attribute that copy to point supports now, didn't exist back then. And a number of other things about copy to points sort of were different back then, where if you wanted to vary what was being copied to each point, you had to create this really complicated for each loop, and it was a nightmare to work with. Copy to points has changed a lot of that since then. The reason I'm saying this is that while the MOPS instancer is great, and it can do a lot, and you'll see that it's fairly simple to work with, it is not the only way to work with MOPS. You don't have to use the instancer to use the rest of MOPS. You can use copy to points interchangeably with the rest of it. I just want to drill that point home as much as I can, that MOPS is not a self-contained system. It will interface directly with the rest of Houdini in most cases. So that aside, let's drop down a MOPS instancer. And then before we go anywhere else, I'm just going to grab my trusty pig head. I'll just run it through a match size so that I can get it centered and scaled to fit, so it's taking up a unit square. And then I'm going to just drag this over to the MOPS instancer. When we put the display flag on, what you'll see by default is just sort of like a 5x5 cube. The main interface here is broken out into 3 points. You have the instancing part, which is basically deciding what's getting copied where, or like what are your copies? What do they actually mean? Then you have your distribution tab, which is sort of describing the points in space, essentially. Like by default here, we're creating a grid. And then the sorting tab is a couple of small things to basically say, like, what do we want these things to be named? Do we want to, give them a name, an ID, a start number, all that stuff, and like, what order do we want them to be sorted in? That's all. So starting from the instance tab, and again, I don't know how my spreadsheet here disappeared, but I'm gonna reopen it. I have a layout here that just has the spreadsheet good to go because I use it all the time. Always have the spreadsheet open. I can't emphasize that enough. So with the instancer, when you wire something in, you can see it's got this multi-input here. And the instancer is automatically going to take whatever you wired in and copy it to those points. If I get something else, for example, I can take let's do a rubber toy, and then we'll just run it through this same mesh size SOP, and then wire it in. This is a multi-input, so you can wire as much stuff in here. I think it's like up to 999 inputs. Now you can see that some of these things by default have automatically been switched over to rubber toys. I'm going to go to the instancer here, and then under the instancing tab, if you go to global transform, I'm just going to turn uniform scale down so that these copies separate a little bit. So you have it's this sort of global transform that you can apply to all of your inputs at once. This is going to be handy if your stuff is scaled in a different way than the distribution allows for, or if you need to just quickly offset everything at once. And now if I zoom in, you can see that it's just randomly taking these inputs and copying them to the different points of the grid that's selected in our distribution method. You can also load in files. So for example, if I drop down a file SOP, I just have default.bgo. I can drag this in and it's automatically going to plop that in too. You can do the same thing with alembics. You can do the same thing with packed disk sequences. Just drop it in and the instancer will put it there. And then by default, it's going to randomly select whatever you want to play there. So if I go to the distribution tab, I can set the type. There's grid, there's a linear option, which is going to put them in a straight line. And you can decide how many points do I want in this? How long do I want this to be? It's basically a line SOP under the hood. You can also decide start end. So you can just give it 2 points in space and it'll draw it between them. You have there's a spherical option. So you can just instance onto an automatic sphere that it'll align them to. So real simple there. You have radial options, so you can instance in the ring. It's just a lot of simple patterns that you can quickly instance to if you don't want to use a copy to points. I'm going to switch this back to the default grid. You can also, and I'll go into this later, but you can instance to template meshes as well. And it gives you some sort of helpful stuff to automatically make those copies stick to animated meshes. So you don't have to do complicated setups to make that work. That's the basics of how the instancer works. Let's just do another quick setup here. I'm going to drop down another pig head and another instancer. I'll just wire this up as the only input. And now I'm going to grab a crag because I want to get a geometry that I want to copy these things onto. And then if you look at crag, if you middle mouse on him, you're going to see that he's packed. And I don't want that. I need regular geometry because I can't scatter on packed geometry because Houdini effectively isn't seeing it as being actual geometry. When something is packed, it's less accessible in a lot of ways. The whole geometry is represented as a single point. And so if you try to run the scatter SOP on that, Houdini's going to get really confused. So I'm going to drop an unpack SOP. And now you can see here, middle mouse, I've got 67 geometries, and that's one for each sort of part of crag. When I unpack, now I've got polygons, so about 90,000 polygons, and this is what I'm going to scatter onto. So I'm just going to drop down a null on this guy to have it. I'm going to call this template. And now let's go back to the MOPs instancer. And in the distribution mode, first, let's go to the global transform and scale these guys down, just to make it a little bit easier because crag is not very big. And then on distribution, I'm going to go to mesh. And it's going to disappear because I don't have anything wired in yet. But what I'm going to do is just take this template and drag it into the template object up here. And now you can see I got a bunch of pig heads glued to crag. With the MOPs instancer, and this is one of the nice things that it does for you, if you're instancing to animated geometry, MOPs by default is going to try and interpolate the attributes of the template so that the instances stick to the surface. So if you've ever tried using a scatter SOP on animated geometry, you'll probably notice that your points will just randomly dance around. The orientation will change, the positions will change. It won't really match from frame to frame. MOPs is automatically, and you can see that there's this checkbox here called Enable Template Interpolation. MOPs is automatically going to interpolate so that positioning and orientation is stable from one to the next. So you can see that I've got this horrific mess of pig heads that are glued to crag here, but they're all going to sort of stay in their same relative positions frame to frame and inherit their orientation from the base model. And you have a lot of other options. You don't necessarily have to scatter onto the mesh. I could instance onto every point of Crag, although this is going to take a second. It's going to be, yeah, you can see like I don't even have enough VRAM to show all these instances at once. We'll go back to that, but you have other options for like how you want to distribute onto meshes. And there's similar settings for instancing to curves, other objects. You also, you have your scatter settings here, so you can change, how many pig heads do I want scattered on this thing? You can, all of the things that you would expect from a scatter setup, like do I want to use a density attribute? Do I want to relax the instances? All of that stuff is, essentially the same stuff under the hood. It's a scatter SOP, but it's just sort of trying to smooth over some of the more annoying parts of the setup for you. In most cases on the instance there, you also have the ability to sort of reorient the mesh or like facet it, or do other quick mesh operations to sort of better describe the orientation of the mesh, because when you scatter instances onto an object, the scattered points are going to inherit the local orientation of your input objects. So for example, if I use a box instead of a template, and I'm just sort of scattering onto that box, oh, that looks weird. You can see that when it's scattering, if I look at the box and actually visualize the normals, you can see that it's got these vertex normals that are, this is hard to describe, but basically if you were to look at the point normal, like if I drop down a normal SOP and create point normals on this, you can see that they're all sort of facing out diagonally. And by default, when you scatter something on an object like this, it's going to read the normal attribute of each point and then sort of smoothly interpolate along that primitive based on where on the primitive the point is scattered. And that's why you end up with something like this when you scatter, is that it's trying to basically point towards the corners and then blend in between. And the way that you would solve that is by basically breaking apart the faces of the points at the corners aren't fused. And that's what a lot of these options are for in here. This is common stuff that you'll deal with in instancing Houdini all the time. I'm just exposing these controllers for you more easily. So like you can just click facet, and now it's going to try and break them so that they or I can also hit reorient. Maybe I want to invert the normal. Maybe I want to invert the up vector. I can compute a completely new one from polygons. There's a lot of operations in here that you can use to basically determine how you want your orientation to work, or you can just do it on the box directly. So for example, I could facet here, break it apart and just say, cusp polygons, or even just unique the points completely, set the cusp angle to 0. Now, if I look at the normals on this, they're going to be completely face outwards. And then I can just turn it off here. And now you can see that everything is sort of facing directly outwards along the surface normal. So it's like each face has been broken apart, so it's not interpolating anymore. So again, you have options. The instancer is just trying to make a lot of this stuff simpler for you, so that you don't have to do it yourself in nodes every single time. The last thing that I want to go over here, not the last thing, but like one other quick thing that I want to go over here is that under the sorting tab, I brought this up earlier, but you have this name prefix and a start number and ID start number. This is sort of an important, one of the few little gotchas with MOPs is that MOPs intends for every point to have an ID attribute, so that when it's trying to match the transforms of things to like line up A and B, it's not dependent on point order. It wants to use an ID attribute. Any MOPs generator, or almost any of them, is going to automatically create these ID attributes for you. So if I click on this and then go to my spreadsheet, you can see that there's an ID attribute, which by default is just the same as the point number. And there's also a name attribute, which is called piece, and then just uses the ID as a suffix. And I could change this. I could just call this like pig head. And now you'll see that everything is going to need pig head 0 through whatever. Where the name attribute comes in more often is when you're doing RBD simulations. Everything needs to have a unique name attribute if you want them to solve as independent objects. So because there's a lot of overlap between RBD sims and instances and packed transforms, MOPS gives you controls to handle this stuff automatically. If you're not using MOPs to create these things. There's another attribute that we'll go into later called MOPs convert that will help just add these attributes for you automatically. But it is important if you're getting unexpected behavior to check and make sure that your ID attribute exists and it's unique for each point. If you're in a situation where like you have two MOP streams, so like let's say I have two templates here, and I'm just going to take, let's see, I'll just have these instanced to something else entirely. Let's just do a grid, the default grid again. Or I don't know here. Oh, I didn't have anything connected to it. That's why. Sorry. So let's change this to a grid. So we've got our basic things here. If I were to merge these together and then sort by ID, you can see that I've got multiple points with the same ID now. And this is where, this is why these controls are exposed to you on the instancer and also in MOPs convert, is because if you have multiple things with the same ID or the same name, they're going to solve as the same object. And a lot of MOPs and other operators in Houdini are going to potentially get confused because they have the same identifier. So the reason these controls are exposed is because if I have multiple streams of geometry going through, I can just say like, you know, let's set the ID start number to 10,000. And now I have a unique sort of, I have this safe separation between the two streams. So if I run other operations on this merge stream later on, you can see that now I don't have duplicate values in the chain. So keep that in mind if you're getting unexpected behavior with MOPS nodes. Like you can see I'm going from 911 here to 10,000. It's just like a safe border between the two streams. This is something that commonly trips people up when they're first starting with MOPS. It's like make sure that you have a unique identifier on everything and use these controls in either the instancer or in MOPs convert to force that separation. One important thing to note when we're going back, let's just go back to this first instance here when we're going to the template geometry. I'm going to set this back to Crag. If you have an animated mesh that you're instancing to that has a changing point count, interpolation will not work. And so if you're trying to use the MOPS instancer to copy to, let's say, particles that are being emitted constantly, an important thing to note here is that you need to turn off template interpolation. So you would just switch that off entirely. If you're using something like an animated sequence like Crag, you'll see that now the points are basically kind of rattling around all over the place and it's not consistent where they're copying to. But in a particle simulation, you would need to turn this off because points are going to be birthing and dying constantly. So again, something to keep in mind. Template interpolation is only something you should turn on if you're copying to a geometry that's deforming, not something where the topology is changing every frame. So real quick, I'm just going to drop down a pig head and a rubber toy, and let's do like a template head. And I'm going to use match size again to just make it, because like these things all have kind of different scales. I'm just going to turn on scale to fit and then copy that to each of these and then wire these into an instancer. So again, this is going to seem pretty familiar. I'm going to take the global transform, shrink it down. So now I've got all these guys randomly instanced here. So let's say I want to be more selective about what's being copied where. I'm going to make a template geometry, and this is what I'm going to copy to. So let me just drop a null down here. I'm going to call this template again. I guess it's going to be template 1 because I already have one of those. Yeah. So I'm going to go to the instancer, again, go to the distribution tab and set this to mesh, and then drag this in here. And so now it's going to be sort of scattering over these points. I'm going to change this to points from scatter. So now it's literally just copying to each of these points on the grid. Maybe let's make this a little smaller so that, there we go. Okay. So a couple of things you're going to notice right away. First of all, the orientation is going to be weird. And this is because, and again, this is going to get esoteric, but it's because the normal and up vectors of the grid are the same, right? This is a grid that's facing straight up. And so the normals are facing the same direction. And that's why this thing is getting confused. There's a couple of different ways that we can fix that. We could change the orientation on here using a MOPS transform. Or we could literally just set, for example, I could go into use a set a point wrangle and set N and up to be whatever I want. But that's why they're facing this way instead of facing in the default orientation, in case you were wondering. Okay, so to set this in such a way that I basically so that I can pick what instance goes where, there's a couple of different ways that you can set this up, but what you need is a sort of an index attribute. And this is, you can sort of think of this as the same as the variant attribute or the piece attribute on copy to points, where it lets you pick what primitive goes to what point. MOPS has sort of a similar helper node to do that for you. The first thing I'm going to do is just create that attribute. And there's a number of different ways that you can do that. But for just as a quick example here, I'm going to really quickly just jump the gun here and put down a shape falloff. And what falloffs do is conceptually, they can do a lot of things in Houdini, but really what it's doing is just setting a float attribute on every point. That's it. And you can see when I click on this, I have this attribute called MOPs falloff, and it's just a float between 0 and 1 on each of these points. If I click preview falloff, it's just going to visualize that as a gradient. So this is all it's doing is the value is 1 here and 0 here, and it's based on this simple shape that I can hit enter in the viewport to grab the manipulator and then change this to adjust those point attributes. And we'll go more into falloffs later. I'll then introduce this other thing here called MOPS index from attribute that basically can take that value, that MOPS falloff attribute, and then remap it into something else. So I have, I'm going to explain more of how this works later, and you could also just use like an attribute randomize. You could use, I think Houdini introduced something in 19 called attribute from pieces, which you could also use. And that's something that works with their new variant setup. But really the important part of this is that you're creating an attribute you're creating an integer type attribute that's just describing what index of the instancer you want to copy to each point. So if I click on this, you can see that it creates this MOPS index attribute, and it's from 0 to 2 based on the value of the MOPS falloff. If I go back to the instancer here, and I'm going to turn off falloff preview so these things don't get colored. If I then go back to the instancing tab and go to indexing mode, instead of random, I can say point attribute. I can also do ordered, and then it's just going to do 1, 2, 3, 1, 2, 3, like just copying to each point in order. But in this case, I can go to point attribute, and by default, it's going to look for something called MOPS index, which is what this index from attribute does. But you can use any point attribute you want as long as it's an integer. Now you can see that based on how that falloff is positioned, it's reading those in. Those attributes from the falloff are being converted to integers based on their existing values, and it's turning into either 0, 1, or 2, which refers to 0, 1, or 2, the 3 inputs that go into the instancer. And now I can actually just move this around, and you can see that it's just going to copy whatever you want based on the input index of that shape falloff. This is just sort of to be like a quick taste of like how easy it can be once you get used to how falloffs work to make big changes to a flow just by moving simple things around. But again, like if you wanted to use any other generator, like an attribute adjust integer or any of those other SOPs that change or set point attributes, you don't have to use index from attribute or a falloff to do this. You can use whatever you want. Okay, does anybody have any other lingering questions about the instancer? It's a complicated node, and I can't go into every single setting for this. I'm just trying to explain conceptually what it's trying to do. But if you have questions about specific things, it's not a bad time to ask. Oh, sure. So if you want to instance to a mesh, if you go to the distribution tab and set the type to mesh, what it's going to do by default is it's going to scatter onto that mesh. But to set it, sorry, I just have to move my zoom window here. You can either use the path selector here and just point to what I want as template 1 and just grab it there, or you can just literally drag this node right in here to set it as a template object. And then by default, this is going to be on scatter mode. So you're going to see it looking something like this, where it's going to scatter a gazillion points all over this thing. And if you want it to scatter, then you can just go below the mesh distribution method here. You can go to scatter, and then this is just like the scatter SOP. So maybe I want 100 points, and it's going to randomly scatter them. But if you want to copy directly to the points of your input template, you just change this from scatter to points. And it also has a few other options here. You can scatter to primitive centers. You can scatter to edge centers. You can turn the whole thing into voxels and then scatter to a voxel grid if you prefer working that way. There's a lot of different ways you can do it. Yes. So this is something that, and again, like the instancer was built before variance existed, which is why some of this might be a little bit confusing. Let's say that I'm just going to copy this over here. If you're used to working with the new variance method, where you would have, let's say, these three objects, then you merge them all to a single stream, and then you would copy that to points. So I have ABC here all merged into a single stream. And what I would do is I would use a name SOP or something like it. You could also do it in VEX to basically just say this object is named pighead. And if I click on the primitive here, you can see that there's a name attribute that's just pighead now. And the attribute, we can just leave it as name. And then I'll copy it to here, and we'll call this toy, and we'll call this head. If you were doing this with a traditional copy to point setup, so I have a grid here, and I want to do copy to points. Actually, you know what? Instead of using a name attribute, we're going to, this will work. It's fine. Anyways, I'll copy this here and this here. And then you're going to see that everything is going to be copied at once to the same point. I'm going to try and pack an instance so that these are all instance. But you have this option to do a piece attribute where I can set this to be name. And now what it's going to look for is on each of these template points, it's going to look for a name attribute that matches one of these three objects. So actually, to make this a little bit easier, why don't I change this to a point wrangle? And I'm just going to say I at variant equals 0. And then this one is going to be 1. And I'm basically just setting a number for each one of these as a attribute, and 2. And now what I can do is essentially randomize this. So do an attribute randomize. And then I'll call this variant, and then set it to be a random number between 0 and 2, 1 dimension. And then actually, that's going to make it a float attribute. This might be easier to do with VEX. I'm sorry if there's like a more modern way to do this. Sometimes I default to VEX by accident because it's just easier for me to think this way. What I can do is say I variant equals 0, 1 rand ptnum. So randomly picking a number between 0 and 2. And then I'm going to cast this to an integer. And so now I have this variant where if I look at my points here, it's a random number 0, 1. I might need to generate a random number between 0 and 3 to make this work. Now I've got some 2s. So I have this variant attribute that's an integer attribute. And then I have it on these as well. And then I'm going to change the piece attribute to variant. And now you have a different one copied to each one based on that random value. So this is sort of the newer way of doing things when you want to decide what object gets copied to what point. If you want to use this with MOPs, if you have like this sort of merged geometry and you want to use this, what you can do is MOPs has this thing called add from variance, where you can, right now it's it doesn't have any inputs and it's copying to a grid. What it'll ask you to do is basically pick that merged geometry. So I'm going to grab merge 2. And then it's going to ask you for what attribute you're using as the variant for this. So I'm going to click this one. And now what it's essentially going to do is create a bunch of object merges. And I apologize for this. I have to sort of lay out the window now. But what it's doing is basically merging those things in and blasting the things that you don't want, and then wiring those in as inputs to the instancer. And then I could grab this same grid if I wanted to with that attribute I set up. So let's go to distribution, set this to mesh. I'm going to grab this point wrangle here as my template. and then change this to points. And now it's essentially going to do the same thing where it's just wiring those copies in and picking. So the only reason to use this really, if you want to use that button, is if you've already got a bunch of stuff configured in the new way where you have like all of your object streams merged into a single stream, and then you want to distribute using the instancer. My advice is if you already have something set up this way and there isn't just another specific feature of the instancer that you're trying to use, just use copy to points, and then you can give it an ID attribute and then just continue using MOPs. It will work either way. Hmm? Yeah, this stuff will all work interchangeably. So it's up to you how you want to work with it, but it's still all point attributes under the hood. It's just sort of using it in a slightly different way. Just really quickly moving on for the instancer temporarily, I'm just going to drop down a new node here. And this is going to be, we'll just call this convert. And again, the original source file for this is included in that zip file. So if you want to dive in and see exactly how things are set up and all the different parameters, you can open the same files that I'm working with and follow along that way. Although I recommend that you drop these nodes down and like play with them to get a sense of how they work together. So tying into what we were talking about earlier with, sometimes you want to use the instancer, sometimes you don't. We have MOPs convert. So just as a quick example here, I'm going to create a sphere. We're going to make it's a polygon mesh by default. And let's say I want to, I'm going to fracture this, and then I want to make each one of these things sort of its own MOPs primitive. So I'll just drop down an ISO offset to turn this into a volume. So now I have a fog volume that I can scatter inside. Sorry, let's do scatter SOP. And let's just do 100. And then I'm going to do a Voronoi fracture. This is, just an old school, simple Voronoi setup. So I've scattered points inside this volume, and now I'm running those to fracture the geometry. So now I have all these individual fragments here. Now let's run MOPs convert. So by default, what MOPs convert is going to do is very simple, similar to what the assemble SOP does, where it's going to take every individual connected piece and turn it into a packed fragment. Without going into too much detail on it, the difference between packed primitives and packed fragments is that packed primitives all have to be the same. Packed fragments can all be different chunks. So you can still have multiple different packed primitives in a single stream. For example, any of the copy to points variant stuff that we were doing before. But the assumption under the hood is that you have lots of copies of a selected pool of objects. Fragments are something that you'll see in any RBD destruction sim. It's very common there. And the idea is that you're storing every possible chunk as a single piece of geometry and then basically picking and choosing from that giant chunk. So fragments are better optimized for things where every piece is unique, but you still need to treat each piece as its own object. I hope that makes sense. But by default, this is what MOPs convert is going to do, is basically take a bunch of chunks of geometry that you have and turn them into single packed primitives. So I have, 1,700 polygons in this first one from this fracture operation. And now I have exactly 100 pieces, like one for each of those points that I scattered. The other thing that MOPs convert does is, again, all the stuff that the instancer did for you. You get the ID start number, you get the name prefix. It automatically is going to generate all of this so that it's ready to go with the rest of the MOP system. And it's also ready to go in RBD sims, like anything involving bullet. So this is what it's doing by default. But there's other ways to use it. For example, let's make a Paul. Sorry, I love messing with these test geometries. I get a kick out of all this stuff. So we've got a Paul. And we've got poor Luis. Both of these guys don't even work at side effects anymore, but they're still getting abused by all of us. And then really quick, what I'm going to do is just, I'm going to use the name SOP to be able to separate these guys. So we'll just call this guy Geo2. And this is because these guys both have like this sort of confusing name attribute under the hood. It's just a quick correction to make up for some weirdness with these things. Don't worry too much about it for now. I'm going to merge these guys together. And now, and this ties back into that original variance question. I'm going to create a grid. and then use attribute from pieces, which is one of these new fancy nodes that Houdini released to essentially do this instancing thing, to be able to pick which one you want. And on attribute from pieces, I'm just going to pick mode random. And what this means is like for each piece attribute that it finds, for each unique name, so some of them are named, you can see that if I click on this guy, or let's just click on the merge, you can see that under primitive attributes, or sorry, I believe it's point attributes. Some of these guys are named, sorry, where is that attribute? Here we go. Here's the name primitive attribute. You can see that some of them are named Geo1, and then the ones under Louise, I manually named Geo2. So this is the variant attribute, essentially. This is what's separating them. So I'm going to grab that name attribute and then just randomly, attribute from pieces is basically giving you a couple of different ways to take that attribute and randomly assign things to it. So it's very similar to MOPs index from attribute. It was just released very recently, but it essentially serves the same function. It's just native Houdini using the way that they expect you to set up these networks. I'm using this as an example because you can take vanilla Houdini copy to points workflows and use these to influence and use these with MOPs interchangeably. It doesn't matter. So real quick, I'm just going to use a point wrangle and I'm going to set my N and up attributes because if you remember when we were instancing to that grid earlier where everything was just pointing in a weird direction, it's because we don't, the normal and up vectors are the same. So there's a couple of different ways that we can sort of just set our orientation to be the default. One way is to say N equals 0, 0, 1 in curly braces like this. And then up is 0, 1, 0. Or you don't have to do both of these. You can do one or the other. You can just say P at Orient, which is I can't even describe what P is supposed to mean in this case, but basically this determines it to be a vector 4 is 0, 0, 0, 1, which is like sort of the default orientation. Either of these would work. I'm just setting this so that by default, all of my points are facing the default way when I do the copy operation. So now, oh, thank you for catching that. It would have been overwritten by the orient anyways. This attribute supersedes these two in the copy to points order. So now I'm going to copy these guys here. I'm going to make sure these are packed so I don't break everything. And then I'm going to set the piece attribute to be the name. And now I've got these sort of random Pauls and Louises everywhere. And that grid, I think my viewport got stuck. I'm sure that's happened to a lot of you guys where the viewport has sort of dead geometry that's stuck in it. If that happens to you, if you have SideFX Labs installed, and I recommend that you do, in Labs, if you go to Help, you can go to Reset Viewport, and now it's going to fix it. Highly recommend Labs and that shortcut because this is a bug that's existed in Houdini basically since its inception. Okay, so the reason that I went through this whole setup is like, again, this is sort of the vanilla way that you would set up randomized copies of things using Houdini 19. It's a relatively new workflow. I can use MOPs convert again because if I go to this copy to points thing here and click on this, I have a name attribute that's set up for each of these, but they're the same, right? It's inheriting that name attribute from the original, and I don't have IDs. So if I tried to run this into an RBD simulation right away, or if I tried to use this with MOPs potentially, it's going to get confused. So MOPs convert, if I go to here and then set the input type here to packed primitives, because what I've copied in here are already packed prims, all it's going to do is give you options to override the ID and name attribute. So because it didn't detect an ID attribute, it's automatically going to add one whether I have the override on or not. And then I can also use this to override the name because I probably don't want these things to all be named Geo 1 and 2. As is, if I had these things with the same name, all the Louises and all the Pauls would solve as a single object in a simulation, which is not what we want. It's going to come in as one giant tangled chunk. So I can hit override name attribute, and now it's actually going to give each one of them a unique name based on the start number and the name prefix that I've set. So if you want to use traditional ways of copying the points, you can do that. And then just if you want to just really quickly and conveniently get things sort of MOPs ready or RBD ready, use MOPs convert and set it to packed prims mode, and now it's ready to go. This is it's almost a viewport glitch. So what's happening is the way that the viewport displays polygon normals for polygon geometry versus packed primitives can sometimes be different, especially if your source geometry doesn't have an explicitly defined normal. So if I fracture this and then click on it, I have vertex normals, but the cusp angle is set in such a way that it's like, it's not going to give you hard edges. And I know this is kind of confusing, but if I can go in here again, and then this might fix it. If I just set the normal angle to be 0, so everything is perfectly hard. Oh no, it's still going to display weird like that, isn't it? Sometimes this is enough. Like if you, for example, if you were to like take a box and then instance that, you'll see this a lot. Like all the boxes will have these weird soft edges. So I'll just take the global transform down. You can see that they all look kind of weird, and that's because they just don't have normals information on them. If I add vertex normals to the boxes, they'll display normally. The Houdini viewport is sometimes weird and fussy about how it describes things that are packed, because as soon as you say that something has been packed, it's a reference. Like now you have a bunch of points in your geometry stream, and each of those points are pointing to a reference of something in your geometry stream somewhere, or even on disk. And the viewport won't always show them the same way. But if this looks weird, but if we go in here and unpack after the fact, we should get our old normals back the way they were. So let's just disable this. Oh yeah, it's cusping for you in polygons. Thank you for that catch. By default, it's cusping the polygons for you when you roll them in, because a lot of times when you're doing these fractures, you don't have normals. I think it's actually might be a recent addition for the Voronoi fracture to create normals for you. I don't know if it always did this, but yeah, that was the issue. Sorry. Nice catch. Okay. Moving on. Another generator that you won't see used quite as commonly as instance or convert is explode. And this is similar to something, I don't know Cinema 4D well, but I'm pretty sure that there's a similar modifier that may also be called explode. But what it does is it essentially allows you to take polygon faces and turn them into individual packed primitives. So I'm just going to create a template head. And then just run this right away through MOPs explode. So I have 5292 polygons in input stream, and coming out of MOPs explode by default, I've got 5292 packed fragments. So each one of those primitive faces becomes a packed fragment packed in place with the centroid of each packed primitive at the center. I don't know if you can see this easily, but you can see that there's like the centroid, the point that represents each one of these packed fragments is at the center of each one of these faces. What it also does is when it does the pack, it orients each face so that it's locally, any kind of transform has sort of a local orientation. Like what do I think forward or positive Z is, or what do I think up positive Y is? It orients each one of them so that they're facing outwards. What that means is if I want to translate something, if I want to translate these like in local space to like make them go outwards, I can use MOPs transform to push them outwards. So for example, I'm just going to do like 0.02, and they're all going to go outwards along the original direction of each primitive normal. So it separates them and then sort of turns each one into an object that you can manipulate with the rest of MOPs as if they were completely separate pieces. You can also optionally use attributes or clustering modes to sort of customize how you want these pieces to be defined. So I'm just going to really quickly go to the explode settings here. And then when you go to define pieces, right now, the method primitive number means that each primitive becomes its own piece, but you don't have to do it this way. You can either give it an attribute, so like provide it with some other piece attribute. You can break each primitive, you can break things apart by primitive group. If you have groups defined on your primitives, each unique group name will become its own chunk, or you can just use the built-in clustering attribute. And what this means is you essentially just say how many pieces do you want, and then define a random seed, and it's just going to randomly fragment them into sort of spatially oriented pieces. Yes, I don't want to go into DOPS just yet. That's going to be for a later lesson, but let me try to take your question one step at a time. When you're defining these clusters, you can provide a piece attribute instead of using the primitive number to fragment each. So I could, for example, generate a random primitive attribute between, let's just call it chunk. So I at chunk equals same thing, fit01 rand primnum, and then we'll fit that between, let's say we want 5 clusters. And then I'll map this to an integer. Actually, let me do this at 6. I need to do this before the explode. And now if I just say my piece name here is chunk, and then go here, it's literally breaking it into 5 different chunks, but it's random. So it's like not spatially oriented, I guess. I could, if I wanted to do this with a falloff, then I could, and like, I'm jumping the gun on falloffs. I didn't want to go into this just yet. But I can take this falloff and then, again, use that index to attribute mode, or I could use attribute from pieces. Either one would be fine. I'll use index from attribute for now. And let's say I want to take that falloff and break it into, let's say, 5 chunks. And it's still called MOPs index. I'll just change this to chunks so that I don't have to change my value later. Now when I go into MOPs explode, let's see, does this need to be a... I've got to promote this. Sorry, it needs to be a primitive attribute, so I'm going to promote it. We're going to promote chunk from point to primitive. And now when I explode, I've got 5 chunks. And when I transfer outwards, you can see that it's breaking apart into 5 pieces. So that's how you would customize it at this level. And then if you wanted to like sort of individually modify each piece, again, I don't want to go into DOPS just yet, but like there's a number of different ways you could do it. If I just wanted to adjust one of these pieces, I could, for one, I could use a group mask and just select it and then scale that down individually, or I could use falloffs to do it. So if I had a falloff after the explode, if I did like a shape falloff, and sorry if I'm going out of order here. The plan was to go to falloffs next. If I create a falloff here and then let's auto fit it, and then looks like it's already vertically oriented. And then scale down, you can see that it's affecting, sorry to erase the group mask. You can see that it's going to affect each piece at a different rate, right? So this is how you would sort of customize those things. But in DOPS, it's a different story. I have to sort of one step at a time. Does that answer most of your question? Okay. Okay. And then moving on, the last one that I wanted to cover here for this lesson is trails. And MOPs Trails is basically a quick way to generate temporarily stable trails from input geometry. So real quick, because this is going on a little bit longer than I had planned. I am going to take a grid here. And let's just make it 3 by 3 to make it a little easier to work with. And then make it 3 columns, 3 rows. So just simple little grid here. And then I'm going to copy this. So copy and transform. And then let's just make 4 copies and translate each one by 1 in Y. So now I've got this little stack here. And then I'm going to use the add SOP to turn these into just points. So add SOP, delete geometry, but keep the points. And now I've just got this sort of little brick of points here. And then I'm going to sort of give you another sneak preview of a modifier called the MOPs noise modifier, which just uses a noise pattern to move packed primitives around. It's really straightforward. But what I've got here is you can see that these things are all sort of randomly adjusted. And I'm just going to scroll down to the bottom here and turn on time varying. And what this means is when I scrub the timeline, these things are automatically just going to be moving around in a noise field. So I've got all these different points dancing around. Once I add MOPs Trails, what it's going to do is for each point, it's going to generate a temporarily stable trail that's automatically going to emit from each one of these things. The advantage of doing this over the traditional trail SOP is that it mostly guarantees that these things are not going to jitter, especially if you have to resample them for any reason. They won't jitter over time. And you have the ability to adjust the output so you can change like the length of these trails. So I can make it so that no trail could be longer than a certain number of units. So right now it's 2 units, and so they'll automatically clip on the way out. You also have the ability to generate, by default, they'll generate clean UVs. So you could run these straight into a sweep SOP, for example, and they'll have clean UVs on them and they'll be temporarily stable. So if I were to sweep these into tubes, for example, and then compute UVs, I don't know if you can see this easily, but as these things sweep, you can see that the UVs don't change. So they'll be stable throughout the entire length of the animation. That's sort of the advantage of using this node. Otherwise, it's really simple. It just generates trails that inherit from what you're doing, but the temporal stability is the big advantage in that they won't jitter when you if you resample them. The disadvantage is that in order to keep things stable so that nothing jitters and so the UVs are consistent, it essentially has to run it needs to run your input points through a solver. So it's not going to be as fast frame to frame as a manual trail setup, but it's just going to be a little easier to work with in the long run. Anyone have any questions about this one? Okay. We're getting a little behind schedule here, so I'm going to move on now to modifiers. Again, you can open up the HIP file if you want, although I recommend following along and dropping nodes if you can. But the file name here is 03 modifiers. And I'm just going to start a new HIP here. Okay, so this is where a lot of the real utility of MOPS is going to start coming in. Modifiers are how you're actually setting the transform intrinsics or the template attributes of incoming geometry. So I'm going to just name this guy transform. And that's the first operator we're going to go through. So let's start by dropping down a pig head. And then I'm going to make a sphere. And then I want to copy these pig heads to this sphere, but I want them to all be looking straight outwards. If I do a copy to points by default here, and I just turn on packet instance and then wire these guys in, by default, you can see that they're all going to be facing in kind of a weird direction. Let me scale down the pig head here so you can see it a little bit better. But they're going to get a little bit confused towards the top. The orientation isn't necessarily consistent the way that they tilt. The reason for this is complicated, but again, it has to do with that same normal and up vector. And when you don't explicitly define normal and up vectors on these copies, Houdini is going to try and guess what you mean by normal and up, and they can't be facing the same way. So you end up getting some strange results if you don't explicitly define what you want the orientation to be. Because this is an annoying thing to do manually most of the time, there's a utility node inside MOPS called MOPS Orient Mesh. And if you drop this down, what it's going to do is essentially generate these things for you. Now, this result, as it is, isn't much better than what we had before, but without getting too much into the math of this, the reason is because of auto up. This is what Houdini does. What it assumes, if you don't have an up attribute, is it's going to try and guess what up should be based on the difference between the surface normal, like so where the normal is facing, and where the default positive Z normal is. So it's going to take that difference and then apply that to up in exactly the same way. 90% of the time, that's not what you want. It's not the right guess. If I turn off auto up and then explicitly set an up vector, so now I'm having them all face towards up, now each of these guys is facing directly outwards along the sphere, and you're sort of getting a cleaner result. I'm just going to take the rows and columns down a bit so we don't have as many of these things, because I want to get like a sort of a clearer picture of what's going on when we start doing the transforms. So now that I have these things copied and ready to go, and I could put a MOPS convert in here to add the ID. For this example, we don't necessarily need that because this is pretty simple. But I'm going to drop down a MOPS transform modifier. MOPS transform modifier is what was one of the nodes you're going to use all the time. And what it's doing is allowing you to use sort of more familiar transforms, like what you see in a transform SOP in terms of being able to define Euler rotations or like basic scales or whatever. And it's going to apply that retroactively to the packed transforms. But a really important note here is that by default, MOPS is going to do this for each primitive in its own local space. By local space, I mean that each of these pig heads sort of has its own idea of what forward is and what up is. And that its internal idea of what those things are is not the same as what world up or world forward is, which is represented by that little gnomon in the corner, this little guy here. So as an example, I'm just going to write a really simple expression here in the rotate y. I'm going to say at frame times 5. So if I scrub the timeline, you're going to see that each one of these guys is spinning locally on its own y-axis, its own up axis, essentially. So they're all going to be moving around like this. This would be extremely annoying to do if you were doing it by hand. If I turn off local space, you can see that now these guys are spinning along world y. So each one of them is spinning as if they were on a stick that's facing directly up as far as the world is concerned. So this is a really important point, like in the way that MOPS is working. It's running for each point, and by default, it's running in local space on all of these things simultaneously. And again, just to drive the point home, if I were to use a traditional transform SOP, a regular transform considers this entire geometry stream to be a single object with a single pivot. So if I use the same expression here on the transform SOP, it's rotating everything at once. So this is the big difference about what MOPS is doing versus what vanilla Houdini is doing for a lot of these transformation operations. MOPS is running in local space individually for every single point that you input. Okay, great. We're just going to do this as a quick survey of other nodes then in the interests of time. So the next one I want to go into is MOPS aim. And this one is sort of like the transform, but it gives you a different interface for how you want to rotate things. So the simplest example to use this for is I'm just going to drop down a pig head like always. I'm going to drop down an instancer. And let's make this a slightly bigger grid of pig heads. So I'm going to turn the global transform down here. And then in order to make it a little bit easier to see what's going on here under distribution, I'm going to change the size here of the grid to be, let's say this big. Let's do like, yeah, about 4. So now I have a few more instances to look at. And now I'm going to drop down MOPS aim. And you only need one input for this thing to work by default. When you first activate it, by default, it's going to be in aim at object mode. And this means that there's a single object that every point is going to look at, a single goal. And you can kind of see it. I don't know if you can see it on my viewport, but there's this little controller here that you can use. If you hit enter, you'll get a manipulator for it. And now you can just drag it around. And every single one of these instances, let me just pivot up here so you can see it, is going to be looking at this same target. This is the simplest way to use MOPS aim, is just everything looks at one single object. I'm just going to take this same network here, copy and paste it. If you don't want to use that default control, you also have the ability to use your own. So especially if you have like complicated pivot structures or something. So what I'm going to do is I'm going to use the control SOP, which just generates sort of generic control objects. I'm going to move it slightly off center so that it's up here somewhere. And I'll change the controls type to circles because I just think that one's a little bit easier to see. And then what I'm going to do is rotate it so that it's sort of spinning around from the center point. That's the reason why I offset it. You'll see this in a second. In the transform SOP, I can use that same expression I used before. So frame times 5. So now this thing is translating essentially, but through a rotation. So it's just going to be moving around in a little circle here. I can wire this directly to the aim target on MOPS aim. So for example, if I go here, I still have this manipulator and everything's looking to the center. But these two optional inputs here are inputs for aim targets or up targets. So I can wire this in here, and it's automatically going to read this and say, oh, okay, this is what you want the aim target to be now. So now if I go in here, you can see that the guide object is automatically snapping on to where this thing was already. And if I drag this, you can see that they're all going to be following that target. And so this means that you can basically any single point coming in from SOPS or packed primitive, you can wire this in and everything will be aimed at that same exact location. Let me just keep going here. So again, I'm going to copy this same network. And I'm just going to do a quick transform stop. I'm going to take these input pig heads here, and I'm just going to move them up by, let's say, 1 unit. So, and again, these are not polygon objects. These are points, right? So I have an equal number of points with the same ID as I do in the original. And if I wanted to, if I don't want to see these points, maybe it's easier to not think of them that way. I can just use an add SOP, delete the geometry, keep the points. And now I just have this little simple point grid here. Now, what I can do is drop down MOPs aim again. And again, I'm going to wire these in as the aim vector. But instead of aim at object, what I'm going to change is this to is aim at points. And so what this means is that each one of these pig heads is going to be trying to aim at the same target that was input to it. Let me just, sorry, getting hung up on something here. And the way that each one of these is going to find that matching point is by using the ID attribute. So again, I have this ID attribute that's unique on each of these points, and it matches those of the original. And now what I can do is let's try another MOPS noise modifier on these aim points. And I'll just turn on time varying again on the noise modifier so that the cloud of points here is like randomly shifting in space. And then what I might do is just turn the amplitude down in Y so that they're not moving in Y at all. So they're just shifting around on that plane. And now if I scrub the timeline and look at MOPS aim, each one of those pig heads is going to individually be looking at the target that matches the ID attribute of the packed primitive. So if I scrub this around, each one of these pig heads is going to be trying to look at that matching point. So you have a lot of control here. Like if you need to be really specific about where each of these packed primitives is aiming towards, you can drive it this way. And I don't go into it in this example specifically, but you have similar controls for managing the up vector. So this third input can accept up targets as well as aim targets. Let's just go back to the first example here to make it easy. By default, it's just going to, if I go to the up tab, it's just assuming that you want a single up vector. So 0, 1, 0, up is up. But it doesn't have to be that. You can also use up to object. And now you're going to get this green square controller. So it's a separate manipulator that you can then drag around. And now this defines the up vector. So all of these things want to be looking up. But if I scroll here, you can see that the up vector is now facing towards this green cube. And this lets you, again, to define any orientation. This is something that's just consistent throughout all of 3D graphics. An orientation has to be described at a minimum by 2 vectors, a forward and an up. So if you're just aiming and you set this thing to its default settings, it's going to assume, well, you probably mean world up to be up. And so everything is going to sort of pivot around as if that's the up vector. But that can get really hairy if your up and normal vectors are too similar to each other. Because as those 2 vectors converge, it starts getting harder and harder to really define like where that thing should be spinning. And that's when you start ending up with instances really rapidly flipping. You'll see like flipping artifacts or like sort of other weird snapping behavior. And it's because rotations become harder and harder to define as those 2 vectors become close to each other. So having the up control here means that you can be a little bit more specific about where you want those things to go. And you don't have to go up to object. You can also do up to points and use the same feature that we used earlier here, where we define 1 point per packed primitive to define exactly what the up vector to be. So you have a lot of control there for like how you might want to aim things or orient them. There's a few other things to go over in here that I don't want to spend too much time on, but basically when you're defining what you want your up and aim axes to be, you can customize this. So if you don't actually want to aim using the forward axis, which is Z by default, you can say like, actually, I want to aim along X. And now the X axis, which is the side for these pigs, is going to be facing at these instead. And you have other similar options for like inverting the aim vector, inverting the up vector. You can also use constrain around up, which is a little confusing, but what it basically means is that if you want things to only aim rigidly, so like, for example, they must be constrained to their up vector, you're going to see that everything is pointing towards this cube here, But if I move this around, you can see that it's almost as if they're stuck on a pin. Like they can only rotate around that defined up axis when they're aiming. So it's a really useful one when you're trying to do things that need to look as if they're rotating on a very specific axis so that they can't freely move about. Or if you're doing like mechanical rigging, things like that, like that's where that constraint comes in.
When you were saying the converging of the world axis and the local axis, why do they even converge in the first place? Doesn't the local override the world when you're doing your rotations?
The axes that I'm talking about are normal and up, which is sort of in Houdini convention. It's the n and up attributes define how things should be copied. And the reason for it is that, and this is more stuff I want to go into more in the math section, is that, and I can just really quickly just set up a wrangle here to show you what this means. You guys don't have to follow along with this if you don't want to. I apologize for this, for leaning on so much VEX here. So really quickly, I'm just making a control here where I can define what n and up are. So n is going to be positive z, the default. Y is going to be, or up is going to be positive y, also the default. And then if I get a bunch of pig heads here and scale them down and then copy them to these points. So, right. The catch is that if these two things are the same, like as they get more and more similar, you can see that it doesn't even change because it's starting to get confused about what these things actually, it's hard to do this with vector controls. How can I better explain this? Without going into math, it's kind of tricky to explain what this means, but essentially, if your n vector, your forward vector, that defines where something is oriented, and your up vector, which is defining how something is facing up, those two things, what you really need are three axes, right? You need x, y, and z to determine how something is truly oriented in space. Using the cross product in math, which we'll go into later, you can take that a forward axis and an up axis and use the cross product to find that third axis, because the cross product gives you an orthogonal vector to the first two input vectors that you get it. So that's like the classic right-hand rule. You have, vector 1, vector 2, and then vector 3 is what you get as a cross product out of it. Those three vectors, that x, y, z, determines how something is oriented in space. If those two vectors are too close to each other, so your n and your up start getting closer and closer and closer until they're like too parallel, you can't get that third vector. And so it's basically a mathematical artifact where once you get too close to that area, that's when you'll start seeing instances start to jitter. Like if those two vectors are animated, like you'll start seeing like shaking, jittering, and then finally like a flip or like a quick snap. That's the reason behind it happening. So the best case scenario is your n and up vectors are as close to orthogonal as possible, meaning that they're perpendicular. I hope that answers that. Sorry that this demo did not work as well as I'd hoped. I'll go more into this in the third section. Okay. So next up, I want to talk about a modifier that you will use easily as often as you use transform, and this is a randomize. So I'm just going to make a new container, call it randomize, and dive in. And let's just mix it up and use the squab for this one. I'm going to pipe it into an instancer. And let's just set we're going to have to turn the scale of this thing way down. So let's turn the global transform to 0.5 and then frame this. So I've got all these squabs. And let's just drop down a MOPs randomize. And what you're going to get is this interface where you can basically just toggle on what you want to randomize. So like I can randomize position and then give it a minimum translate and a maximum translate in each of the three axes, and then pick a seed and it's just going to randomize them. Orientation is even easier. Just click it and they're going to be randomly oriented in all three axes. There's a separate seed for this, so you can just dial this in however you need to. So that's all this is meant to do. I can go down to scale. You can either randomize scale in all three axes, or you can individually, or you can just do uniform scale and then set your minimum and maximum, adjust the seed. It's pretty straightforward, but it comes in handy in a ton of different situations, because you're always going to want to add randomness or some amount of chaos to make your sim feel more natural. Just to make things a little bit more complicated, let's drop in another Paul here. And then I'm going to instance these guys in, let's do a line this time. So I'm going to go to distribution, change this to linear, and change the length of the line so that we've got these Pauls kind of spread out here. Let's just do 10. And then to randomize this again, and I'm just going to randomize orientation on a single axis. So I'm going to turn off I'm going to set the minimum and maximum to 0 on X and Z so that he's only spinning out on Y. One of the important parameters here is the step parameter, because there's a lot of cases where you're going to want to randomize things, but you don't want things to be 100% random in every axis. You want to be able to constrain it. The step parameter operates in degrees. So if I set this to, let's say, 90, now you can see each of these Pauls are facing in one of 4 cardinal directions. So you can lock the amount of randomization that you want to a specific step. I could change this to 45, and now they're going to be locked to 45-degree angles. The same thing applies to position as well. So if I want to randomize and have some of these guys be exactly 1 meter above the others, I'm going to set my translate maximum to 1, and then set my step also to be 1. And now you're going to get some that are popped up a meter and some that aren't. Just to drive this home a little bit further, I'm going to make another Falloff here. And this is something that I'll go into more when we start talking more about Falloffs. I'm just going to turn off the position Falloff to make it a little bit easier to look at. I'm going to hit auto fit on this, and that just means that the shape is going to be distributed along the entire line of things here. And if I preview Falloff, you can't preview on this. But basically I have like a 0 to 1 shape going on here. I'm going to drop down another randomize. And this time I will randomize, let's just do scale. So, and let's just adjust the seed to whatever. You can see that this guy isn't changing much, but these guys are changing a lot when I adjust the seed. And that's because by default, all of these modifiers are looking for a falloff attribute in order to decide how much of the effect that we want to dial in. So if I turn off falloff, you can see that everything is being evenly randomized. But if I turn it on again, I can take this shape here and move it back and forth. And some of these guys are going to start shrinking more than others based on the value of falloff. If I move this shape all the way over here, everything has a falloff value. You can look again, check the spreadsheet of 0. Randomize won't have any effect. So this is something that we'll go into more when we start talking about falloffs. But all of these things can be modulated. All the effects of all of these nodes, with few exceptions, can be modulated by a falloff attribute. So I'm going to just jump out and then make a new geometry network. And we're going to talk about the noise modifier, which is also another really handy one that can get you a lot of cool effects for cheap. So we're going to start with the template head. And then I'm going to just run a MOPs explode on this. So we're going to break the head up into individual fragments. And we can probably just leave this at the default settings. I don't necessarily think we need to do any clustering or anything. So by default, if you drop down a MOPs noise modifier, and then we're probably going to have to adjust these settings because I think this is going to be pushing these points out. Oh yeah, it's like moving them way too much. So I'm going to scroll up here where it says effect position. I'm just going to scale this way back. So 0.03 roughly. So that it's changing a little bit, but not nearly what it was. And then I'm going to go to the noise properties here and just change the frequency to be a little bit higher because we're dealing with a small object. So let's just do 6. So by default, what it's going to do is apply the noise. If we scroll back to the top here, if we scroll down to the noise properties, the noise signature is vector. And that means that it's the noise field, whatever function that you pick. In this case, I'm using curl noise, but you have a lot of different options for what noise function you want to use. It's going to move each one of these packed primitives according to that noise field. And you can use the amplitude controls to dial in individually, like how much you want the noise to affect it on each axis. So this is sort of like the straightforward way of using it, just apply noise. And then you can, like if you ever used VOPs before or any other attribute noise, there's like offset values and you can sort of animate these in order to make the noise field move. This is sort of the simplest way to use it. If I take the same function, and I'm just going to set the noise signature to float instead, what this means is that each piece is going to be moved outwards along that same noise function. So if I move the offset here, what it's essentially doing is acting almost like a peak SOP, where everything is going to be moved along its local Z. And that includes points. You could apply this to a mesh if you wanted to. Like, for example, if I just took this original template head without the explode and ran it through vector mode here and just animate the offset, you can see that it's essentially doing the same thing, although I don't have normals computed. So I'm probably going to have to do this and then apply the normals to the points on the normal SOP. And now if I animate this, you can see it's kind of acting like a peak SOP, but with a noise function. The other thing that I want to show you is, we can just go back to this example. Down at the bottom of the noise field, rather than having to animate the offset parameters, there's an automatic little setting here called time varying. If you turn this on, it's going to make the noise function automatically evaluate or automatically vary over time. And the speed of it is determined by the time scale parameter down here. So if I turn this to like 10, it's going to make the noise field that much faster as it evaluates. The other really handy thing here that you should know about is looping noise, because we all love those looped Instagram videos where everything just makes a perfect seamless loop every time. If you click on looping noise, you can define a loop period. And this basically means the time in seconds in which you want the noise function to recycle itself. So if I, 2 seconds at the default 24 frames per second means that it's going to take 48 frames to loop from one to the next. So I'm just going to set my timeline to be 47 and then play through this. And you can see that it's going to make a seamless loop. So you can set this loop period to be whatever you want. You can mix that with time scale and mix that with the other parameters of the noise in order to get seamlessly looping noise, which is going to really help if you need to be really precise about your starting and ending point for a particular sequence. And then just one other thing that I want to show you here before we move on. I'm going to just take this same setup here with the explode. I'm going to make another noise modifier using roughly the same settings. But I'm going to go up here to where it says mode. There's 2 ways to use the noise modifier. You have simple mode, which is what we're seeing, which is effectively fully procedural. And then we have advect mode. And advect mode, if I turn this on, basically treats this like a solver. So at the beginning, we're not going to see anything because we haven't run any time steps yet. But with advect mode on, I think I'm going to leave the rest of the settings where they are, but I might add effect rotation. Now, as I drag the timeline, what it's doing is it's running all of these pieces through that noise field over time. Let me just extend my timeline so we can see it. Do this better. So this is effectively a simulation at this point. It's going to take these things and move them through that noise field over time. I'm going to turn off loop time varying. Now we have a static noise field. And so you can see it's like these pieces are eventually going to take the shape of that curl noise field and move through it over time. The orientation bit of this, when you're in advect mode, is affected by aim weight, which is sort of an easy way of saying, like, how much do you want each piece to point towards the direction of motion over time. If I turn off effect rotation completely, I can just, you can see that all it's going to do is just move the pieces. It's translating them over time. But effect rotation will blend the direction of motion into the noise field, so you actually have these things aiming towards it. So you can, it's almost a particle simulation at this point, where they'll point into the direction of flow as they move around. Does anyone have any other questions about this? Not really. The usual MOPs sort of limitations apply where like you want to make sure you have an ID attribute just in case. The MOPs noises, a lot of them, not all of them, some of them are default Houdini noises, but some of them are custom. There's a few noise functions in here like the mix minima noise or the mosaic noise that are custom. And so I can't guarantee that they're going to run as quickly as an attribute adjust noise will. Also, the time varying option requires two separate noise functions to be calculated and then blended into each other in order to work. And so it's going to naturally be slower because it has to evaluate the noise function twice per point instead of once. But that's really it. Otherwise, these are effectively the same thing. And in advect mode, you have a couple of other like convenience options that might help you. You can, instead of using the MOPs trails, you can automatically drop trails out of this if you want to, if you enable output trails. And there's a few other sort of convenience nodes in here that are for you, but you could just use attribute adjust noise on the points instead if you don't care about rotation, and that would be fine. Yes, absolutely. So if I go to this, let's just go to the procedural noise modifier. This is the next section really, but if I only want to affect certain parts of this, again, I could use the simplest fall off that I have is or one of the simplest is the shape fall off. Sorry. And so I could, let's just auto fit this. Looks like it's roughly vertical. Yeah, okay. So now if I run the noise modifier on this, you're going to see that the points at the bottom are going to be affected more than the points at the top. And I can adjust that based on, the position and orientation of this control. So like if I only want to affect, I could flip this upside down and then only affect like the top of his head. Maybe move this up here. And now if I animate this, you can see that it's only affecting certain parts. So almost every modifier that you can work with respects fall off in one way or another. And I'll go into that in a second, but you can be really specific about how you want to define what the fall off attribute is or what it looks like and how it affects things. Does that answer your question? Okay. So now I want to go into the last big section of this, which is the fourth file, 04 Falloffs. This is sort of the other main category of MOPs to talk about. Just a second. Got to open this file in the background. Okay. So I'm going to make a new container here and then drop down a Paul. And then let's just instance him really quickly. And let's say, I don't know, how many do we need? Let's do a global transform of about a quarter of what he is now. So let's do 0.25. Yeah, that seems like it'll work. Okay, so first let's drop down a MOPs transform modifier. And I want to, let's say, rotate these guys 90 degrees on Y and scale down by 0.5. So now I have all these little Pauls. On any modifier, you're going to see this option called do fall off. And that means, do you want to apply fall off to these things or do you want to affect them uniformly? And then you're going to have this option called fall off attribute, which is, this is any point-based float attribute. So any number between 0 and 1 that you want to use as the weight of the operation that you're applying. Right now that attribute exists, but if I go to MOPs fall off, you can see that it's 1 for every single point here. And that's generated by default by the instancer. It just sets a default fall off so that if you apply a modifier without being specific about it later, everything gets affected. But if that fall off attribute exists and it's different per point, it's going to affect how this thing behaves. It's just a sort of a scale applied to every modifier operation. So the simplest fall off that you can create is the plain fall off. And this is just sort of it's so simple that it's really just a little convenience node, but plain fall off basically just sets that attribute for everything at once. So I have this fall off value here and I can scale it. And you can see that as I scale it, the effect of that transform scales the same way. So if my fall off value is 0, nothing happens. If it's 1, the full weight of the operation happens. So pretty boring. From this instance there, let's just drag it over here. And then let's make a shape fall off. And this one I've already shown you guys a few times as far as how it works and what it does. But I'm going to click on this. And then you can see you've got, and I don't know how easily you can see this on my monitor, but you get these 2 blue squares. And this is essentially the handle that defines the fall off. I'm going to take the same transform and copy it after the fact, and then put this on so you can see what's going on. You can see that it's already, each poly is being affected differently based on where it is within that shape. If I click on this shape fall off here and click preview fall off, what this is going to do normally, and this is sometimes hard to see because this guy already has a shader and Houdini's viewport can be a little bit weird. Let's see, can I delete? Yeah, let me just run an attribute delete on the material so that we don't see it. Hopefully that'll make this a little bit easier to see. Okay, for some reason, my viewport is not wanting to display color right now. And so this is a good. Oh, yeah, there it is. Thank you for pointing that out. If you're in a situation where you can't preview fall off, and most commonly it's because of the issue that Armin brought up, or it's because you're working with packed fragments. Again, if you were to like run a shatter sim and then pack it as fragments after the fact, Houdini's viewport cannot see vertex color accurately on packed fragments. It just won't work. Or I'm sorry, it can't see the point color attribute in the Houdini viewport. If you're applying it to packed primitives, you can see it per primitive. But on packed fragments, the point color attribute can't accurately affect the color of packed primitives. They'll all turn the same color at once. So when you're in weird situations like this, where for whatever reason you can't preview color, under Falloff preview, we have this option called display as sprites. If you turn this on, and then you can adjust the scale. Like right now, Paul's scale is a little bit weird. These sprites are aligning themselves in a strange way. You can sort of change this or override it entirely and then just drag this down so you can see what's going on. Falloff preview is just there so that you can see this accurately in situations where the viewport won't allow it to happen. If I go back to shape here, I can hit enter to grab the manipulator and then move this around, and you can see that each point is changing colors based on the Falloff preview ramp. I'm just going to turn off the display of sprites because it's working now in the geometry. So if I highlight the transform modifier now to look at this geometry, and then I'm going to turn off Falloff preview. And then I'm going to click in the view here so that the preview geometry turns off because it's really annoying, but I still get my manipulator. And now I can just drag this back and forth, and you can see that the position of the shape and also the orientation affects how that fall off is applied. And if you click on the shape fall off, there's a lot of different kinds of, let me just go back here and turn on preview again. There's a lot of different shapes you can use. Linear isn't the only option. I can use spheres. And so now I have a sphere shaped fall off that I can move around. There's an inner and outer radius. You can affect sort of the width of the fall off effect. There's a box. So if you want to do use sort of a volume where you have an inner and outer cube, there's a torus. There's a radial wipe, which you can sort of use to define, you define an angle range. So if I turn this up, it sort of fans out, and then use this to control the spread, either fanning in or fanning out. So there's a lot of different options you have for just really quickly creating these values. And I want to emphasize that this is just a point attribute. There is nothing special about MOPs Falloff. There's nothing special even about the name. So if I were to, let's just change this back to a spherical one just to be simple, and then look at this modifier, and you can see that, especially if I exaggerate this, the guys on the inside are being affected more than on the outside. If I go to this fall off attribute here and I call this, foo, you can see that now all these guys are being manipulated the same way. But all you need to do is just make sure that the fall off attribute matches. What this allows you to do is not only use multiple shape fall offs to mean multiple different things without interfering with each other, because it's a really common problem where you might have multiple fall offs kind of stacked up on top of each other, but you don't want them to interfere with each other. This allows you basically affect them as two completely separate streams. So you can line this up. What this also means, though, is that I could use, for example, attribute randomize instead of the shape fall off. And I'm just going to, I can call this whatever I want. So now this is BAZ is my attribute name. I'm going to define it as a one-dimensional uniform value between 0 and 1. So if you're looking here, then BAZ, it's like all of these numbers. And then if I set this, now everything is randomized. And I can go here and adjust the seed, and it's affecting it the same way. So Falloffs are really convenient for spatially setting float attributes that go between 0 and 1, because that's what MOPS wants to see when weighting operations. But you are absolutely not limited to using MOPS operators to do that. All it wants is a float point attribute, and that can be anything that you want it to be. Let's keep going with other falloffs. There's also noise falloff. And this one works a lot like the other noise operators in MOPS, where, let's just turn on preview falloff, where you have a bunch of input noise functions. They're all one dimension, or they're all float noise in this case, not vector. And you have those same controls for, amplitude, frequency to turn that up. You can make them time varying automatically. So now you can see that it's going to cycle over time. And then again, I can just grab this transform modifier and paste it here. And let's turn off falloff preview. And same deal, right? So you're just using a noise function to change the effect. And this way, especially for simple things like where you want to affect only one channel, or you don't want to affect rotation the same way as position, you can just define position A, position B, and then use noise falloff to randomize it to get your more organic behavior. Another thing that I should point out is that almost every falloff function comes with built-in controls for remapping. So if I go to the remap function here and then enable fit, this will be easier to see if I turn on falloff preview. If I turn on fit, what I can do is just set an input and output min and max. The output min and max, you're rarely going to change, because most of the time falloffs you want between 0 and 1, but the input can help, especially because every noise function, its minimum and maximum range is a little different. Some noises are clean values between 0 and 1. Some are between like 0.2 and 0.8. Some are between negative 1.7 and 1.7. It really depends on the noise function, and it's not something that you can necessarily always know. But what you can do here is basically just drag it until you start seeing those dark blues. That's your minimum. Drag this until you start seeing things close to white. That's your max. And it's a little contrasty, but it should work. And you also have a ramp that you can use here, so you can fine tune exactly how you want that interpolation to work. And that's all built in for you. And now apply this to the modifier, and you get, now our noise function is a lot more pronounced, and we're getting like good peaks and valleys in the final effect. The last thing about the basic falloff stuff that I want to go over here is falloffs all have blend modes built in. So again, I'm going to take the same exact transform and wire it in here, and then wire this noise falloff into this plane falloff. So if I set the blend right now, because the plane falloff is set to 1, it's really not affecting anything. And I'm just going to turn off this preview again because it's getting in the way. But you have blend modes here. So let's say I like this noise function, but I want the whole function to fade out over time. What I can do is just set this to multiply. And then now that it's multiplying, I'm getting the full effect of the noise function, because whatever it was times 1 is the same. But now I can dial it back. And so you could keyframe this one attribute as a multiplier over the entire thing. And that's any falloff. So if I wanted it to only multiply within a given spherical area, I could do it that way. All of these blending modes are built into every single falloff node. MOPS combined falloffs is that blend mode, but exposed. So internally, if you look inside any of the MOPS nodes, it's using MOPS combined falloff to do it, but it's there as its own node for you if you want to do it that way. There's a number of sort of lower level tools that you see that you won't usually use by itself. Like, for example, preview falloff is its own node that you can drop down if you want to, but every falloff has its own preview built in. So a lot of these tools are actually for me to use so that I can copy the same preview logic into every single HDA and not have to rework it. Chops is, I don't want to go too far into chops in this just because that's a completely separate topic. But in the end, if chops are affecting point attribute values, that's all you need. So you could either generate a signal using chops, or you could take existing attributes, like existing animated, MOPs noise or MOPs transform attributes, import those attributes into chops, process them through a filter or a jiggle or a bounce or whatever it is that you want to use. And then once you're done, use the channel SOP to read those values back in as a float attribute and then apply that as a fall off. That's totally valid. I can't whip together an example for you in the space of this class because we're already running over time. Fall off nodes. So I'm going to jump out, and this is going to be the spline and object fall offs, which are sort of more complicated ways of generating fall off values. So real quick, I'm just going to make a box SOP, give it some vertex normals, and then I'm going to make a grid. And I'm alternating between copy to points and the instancer just to sort of double down on the fact that you can use either. You are not limited to one or the other. You can do this any way you like. So I've got this grid of boxes here. I am going to, let's see. The next thing that I want to do is just draw a spline, something that's going through this grid here. So I'm going to use a curve SOP and just draw, anything. It doesn't really matter, just something. The next thing I'm going to do is resample it because right now it's coming in as a Bezier curve, and MOPS sort of as a convention wants to work with polygons and packed primitives. It doesn't really understand NURBs or Beziers very well. So the resample is going to turn this into polygons. It's just a really quick, easy way to do it. And then I am going to drop down a MOPS spline fall off. And your packed primitives go in here, and the spline goes in the second input. And if I turn on preview fall off, by default, what it's going to do is define your fall off based on the distance to the spline. So uniformly throughout the entire spline, you have a minimum and a maximum distance. And I can crank this if I need to. And this basically just determines sort of the amount that it's going to fall off. And if I use like a transform operation here and rotate this along Y, you can see that it's just really all it's doing is taking the distance to the spline and using that as a fall off. You have more advanced options for this though. For example, you can use distance times curve position. And this is good if you're trying to sort of show something changing over time as it reaches the end of the spline. Distance times curve position basically means, and I'm going to probably up the minimum distance a bit to get this. No, that's not going to work. What this means is basically one side of the spline is going to be full power, and then it's going to fade towards the back. So this is the front, this is the back. And in terms of the curve weight, this is the front end, this is the back. So I can sort of taper this off to make it, maybe a little bit more nicely faded here. And now if I rotate this, it's the same deal. It's going to weight one end of the spline heavier than the other in order to generate your fall off. You also can just do it by curve position alone. So if I drag this way down, and you can see it's this one is harder because this thing is probably a little bit oversized compared to what we would need it to be, but it's basically making this fall off relative to the curve position alone. I probably need to, this actually may be a bug. I'll look into this later because it looks like these controls aren't being respected. So apologies for that, but that'll be fixed in the next build. I'm just going to go really quickly over to the object fall off because the spline fall off has less settings on it. It's not really that complicated. So let's take the same setup here. And then I'm going to make a pig head. And it should be right in the center here, but I think I'll scale it up a bit. So let's make this have a scale of about 4. I'm going to translate him up a little bit and then move him, just centering him a little bit better here. And then what I'm going to do is make a transform SOP. And all I wanted to do is have this guy just kind of spin in place. So I'm going to set his rotate Y to be time times 100. So now he's just spinning around. Next, I'm going to take all these packed prims I made and run them through a MOPs object falloff. And then turn on preview falloff. And so you can kind of see what this guy is doing is that based on the position relative to the mesh, like what's contained, it's going to set the falloff based on that, and it's going to update over time. By default, your area of influence is the inside. And I can just turn the radius up here, and you can see that it kind of fades up this over time. But you can also go outside, which is essentially the opposite. So if I turn the radius here, you can see that anything outside the mesh will have the maximum falloff value. You can use the distance from the surface, which means that it's going to essentially be like a signed distance field where it doesn't care whether it's inside or outside. It only cares about the rough distance from the field. You can also use volume samples. So if you have a scalar volume, like a fog volume, and you want to sample that directly to use as the falloff value, you can do it that way. And point cloud will essentially take a completely disconnected cloud of points in Houdini and use the distance to the nearest point in order to describe the falloff. So you can get pretty specific about how you want these things to be organized. Another thing to note about this really quick is that most falloffs also have built-in noise functionality. So to make this a little easier to see, I'm going to just give myself some more rows and columns here and then just turn down the size of the box a bit so that we can get a higher resolution noise field. If I click on add noise, you can see that it immediately just scatters the effect of the falloff here. And this applies to shape, it applies to object. Pretty much any falloff node has built-in noise functions with all of the same controls that you're used to seeing before, including time varying. So we can just click this, and then now we have this sort of, let's disable this transform here. And now we have an evolving noise field over time that we can use to like randomly affect these primitives in a more natural way. And just to show kind of a little bit more about what this does here, I'm going to disable the noise real quick here, turn this back on, and then disable the falloff preview. And let's drop down a MOPs transform modifier. And just say, let's scale these up by 10. Now, let's see, why is it? Okay. Again, because the grid is facing up, it's that same orientation problem that we keep running into. I'm just going to set n to z and up to y, and this is something that you'll run into constantly in Houdini. You could also potentially use MOPs Orient Mesh to handle this. And you can see that now it's scaling according to that pig head rotating. If I template this geometry, you'll see that it's doing this. One quick thing here is if you don't want these guys to be scaling from the center point, I will go into this node in more detail later. But we have this thing called MOPs pivot, where I can set the mode to be aligned to bounding box and just set it to Y minimum. And you can do this after the fact. So you can adjust the pivots without changing the positions of the packed primitives or like adjusting their orientations. So I can just set it to be minimum Y. And now when I run the transform, everything is scaling from the base. I'll go more into this in the second lesson, but this is a good one to know about in terms of being able to quickly adjust pivots. Okay, moving on. Are there any questions about those before I go to some of the other falloff concepts? Okay, I'm going to take that as a no. So now I just want to talk really quickly about transformed falloffs. And this is not something that's that widely used, but it is extremely handy for certain kinds of operations. So I'm going to just make another box and give it vertex normals and then make another instancer. And let's just set the global transform down a bit. And you know what, let's set this to fixed number instead of fixed size, just to show off a different distribution mode. So what this allows you to do is basically pick a spacing. It's just a different way of looking at the same problem, but I can pick the spacing and then just say exactly how many clones I want on each axis. So I'm going to turn this up to like a 20 by 20 grid. Now, let's say I have a shape falloff, like let's do a sphere. And I'm going to turn on Falloff preview so that we can see it. Set the Falloff type to be spherical. And now I have this little sphere, but what I really want to do is have it rotate around the outsides of this thing. And that's kind of hard to do. Like I could use, sine and cosine on the translates for this thing in order to have it sort of spin around like this, but that's kind of a pain to do. So instead, what I'm going to do is similar to what I did with the aim control earlier in that demo. I'm just going to move this guy over here, and then I'm going to drop down MOPs Transform Falloff. Don't confuse this with the MOPs Transform Modifier. This one's slightly different. What this allows you to do is essentially use a separate anchor to describe the orientation. So I've already made this offset from the center for this shape. I'm going to wire the transform falloff into the second input of this falloff. Most falloffs have this second input specifically for this node. It's looking for this transform falloff modifier. What this then allows you to do is then set an expression or a separate function on this. So I'm going to, again, use that simple frame times 5. And this is going to act as sort of a pre-transform on top of the existing one. So now when I animate this, you can see that it's spinning around the center. This is going to allow you to get a lot more complex behavior from without having to do fancy expressions to do it. And if I want to change like the distance this is going at, I could just keyframe this one control as it animates and get like kind of really chaotic bouncing behavior from it. The other thing that you can do is if you have multiple falloffs, like let's say you're keyframing a lot of different falloffs in a row, but you want them to all move the same way and not have to do channel referencing, you could drop down a bunch of different, falloffs in a row and just chain them all to the same transform falloff, and they'll all transform in exactly the same way. So you can use that to quickly link these things together. And then that way, if you want to make an adjustment, you can just adjust them here without having to set up complicated channel reference networks or anything like that. Okay. So for this next one, I want to show off spread falloff, which is a really handy one. If you've ever looked at any old tutorials about infection solver, sorry about that. Okay, so really quick, what I'm going to do is set up a geometry that I want to spread over. So again, what this is meant to do is sort of replicate that infection solve effect where you have sort of an effect of some kind spreading from one piece of geometry organically to the next. The nice thing about MOP spread falloff is that it doesn't use a solver. So you don't have to do any kind of fancy solver SOP stuff. The entire thing is procedural and it solves pretty quick. So we'll start with a squab, and then I'm just going to, so what I want to do is just remove all attributes from this thing, just like wipe this out so I don't get this. And then I'm going to just name this template because I'm going to be using him a few times here. So let's start with a box and then an instancer. And I'm going to go to the distribution mode and set this to be mesh, and then drag this template in as the template object. And then to make this a little bit easier, what I'm going to do is set this, let's set this to a different one. Instead of Vesh, let's do, instead of scatter, let's do voxels. And so now I'm getting like sort of a voxel grid effect. I'm going to change the voxel size to be a little bit smaller. And instead of scattering, I'm going to switch this to voxel grid. And if I go back to the instancing tab and set the transform down, what it means is that I'm going to get this pretty dense array of bricks. So this is just like, again, another way that you can use the instancer in ways to distribute things. I'm going to turn on vertex normals for this so we get this sort of clean look. And I'm doing this because it's just going to be a little bit easier to see the effect of the spread in this case while we have this active. The next thing I do before I get to the spread falloff is I need to define a starting point. And there's a number of different ways that you can define where you might want the starting point to be. One of those is by making a group. So what I'm going to do is create a sphere, and I'm going to sort of use this as my control to define where I want the start of the spread to be. Let's just move this guy, let's say, over here towards the tail. That should be good enough. Then I'm going to use a group SOP. And I'm going to set this to, I want a point group, because again, MOPS likes to operate on points. I'm going to tie this sphere into the second end. And then I'm going to turn off base group and then include in bounding regions. I'm going to set this to bounding object. And so now if I look at this, I've got 82 points in group one, which is fine. That ought to work. I'm going to name this group start. This is going to be the start of the spread effect. Now I'm going to use mop spread fall off. And let's turn on preview fall off because this one takes a little bit of work to tune. So what it wants to know is where do you want the fall off effect to start from? And then it's going to automatically find all of the ends. So by default, it's going to look for a group mask. You can also use an attribute. There's a few other options for it, but the group mask is the simplest way. And I'm just going to call it start. So now with that set, if I go to the animate tab, this is where it's actually determining the motion of the spread. And so you're not going to see anything right away. What you need to do is animate this parameter here, spread. And if I drag it across, you can see it's going to spread from that one area and then push out to the rest of the model. There's a couple of different ways that this can work. Your distance metric, this is important, can either be radius or connectivity. When you're dealing with a bunch of completely separate packed primitives like we are right now, you really don't have any choice but to use radius because there is no connectivity between these points. And it means that the way that the spread works is sometimes going to jump over joints and things like that that you would normally expect because there's no connectivity sort of influencing how the spread is going to direct. It's just going based on radius. The way that it determines connectivity between things when you're in radius mode, the way that it determines the spread order is through sort of a search point. So what it's going to do is for every point that you have, it's going to look for nearby neighbors within the search radius that you determine. And then say, oh, okay, you're my neighbor. I'm going to spread to you next. So it's automatically generating sort of a network underneath this that's saying like, here's my neighboring points, like a lattice almost. So as you spread this, it's going to spread over the entire length of this, and you can kind of control how much it tapers using the fall off width. If you're trying to do one of these operations and you notice that there's an area that's not being spread to, that's often a function of your search radius. So if your search radius is too low, you can see that it's going to struggle to figure out the spread because you're not giving it enough room to look for neighboring points. You can see that as this goes up, it gets more accurate results. The downside for having a higher search radius is that it's a little bit more expensive to calculate, but it only needs to calculate this once. Again, this is fully procedural. So once you've calculated the effect of the spread, you can animate this back and forth and you don't need any kind of solver. Like the rest of Falloffs and MOPs, you have noise too. So you can sort of get more organic behavior by enabling noise. So it kind of creeps over this thing a little bit. And all it's doing is just adjusting the position of these things before it computes the network. If your noise function is too strong, it's possible to break the connectivity between these 2 points if you're using radius mode. And so you might need to increase your search radius. And like anything else, yeah, now we can go into the transform modifier. And let's say we want this thing to like, appear over time. I can just turn the uniform scale down to 0. And then what I really want for this thing to do when I'm animating it is I want it to, let's say I want it to appear instead of disappear. Remember that each one of these falloffs has built-in remapping controls. So I can just turn on fit and then set my output instead of 0 to 1. I can set this to 1 to 0. And now I've just inverted the effect. So if I go to my spread falloff and animate this now, the thing is animating on. Moving on to the next one, I'm going to use this same template. And I think actually it'll use the same start group as well. Let's grab this. Let's just copy this whole thing. And what I can do in this case is actually, you know what? Let's just use the template directly. So now I have a group of points here. And I'm going to start with the same start group. So the setup is the same, but now I'm working on the geometry itself instead of working on packed primitives. And let's drop down another spread fall off. And I'm going to change the distance metric to connectivity. And so if we enable preview fall off on this and spread, let's see. I think I need to change my distance somewhat. Oh, I need to define my point group. That's what I missed. Okay. So now the difference with connectivity is you're going to see that in the previous demo where it sort of spread a little bit more evenly left to right, you can see that here it's crawling up the legs before it makes it down the other side. It's like paying a little bit more attention to the input geometry. This is sort of the advantage of using connectivity data is these things actually, it's jumping from vertex to vertex based on neighbors that are already established on the mesh. And you can layer the noise on top of this as well. You can do all of that same stuff, but you're going to tend to get more reliable sort of creeping behavior when you're doing something like this. And again, these are effectively template points, right? So if I wanted to, I could set the MOPs transform modifier on these points the same way. And let's just do the same scaling operation. And then I'm going to grab a box and give it vertex normals. And then let's just set the uniform scale to 0.1. And then I could even scatter after this transform operation. I could scatter points onto this thing and then copy them. And because those scattered points inherit all of those same template point attributes, if I copy to this and then do one of these, now when I go back here and animate the spread effect, the scale attribute that's set on the template mesh is inherited by those scatter points, and the boxes use those template attributes when they're being copied. So if I animate the spread, I can get a similar kind of effect, but now I'm getting this connectivity. And you can see that it's a little bit slower to operate because Houdini has to go down this whole chain and recreate it every single frame, which is one of the advantages of using the MOPs method of setting the attributes afterwards is depending on how complicated your network is upstream and how many clones you have, it can sometimes be faster to work backwards and just generate all of your geometry once. And then for every future time step, the only thing that you're doing is setting the intrinsics instead of generating your entire network over and over again. That's something to keep in mind is time dependency is a really big deal. And if you don't have that badge on, usually I have it on, but that's something that you can turn on by hitting D in the network view, going to badges, and just making sure that you have your time dependent badge on. If you have it hidden, don't. It's very handy. But what this will let you do is sort of see whether or not certain nodes are being calculated on every single frame instead of being calculated once. Just a little aside there for you. Spread falloff is also something that you can use in conjunction with another quick little modifier that I want to show you that I didn't bring up before. So here's our classic pig head. I'm going to do a spread falloff. And if I don't want to define an explicit group for the start points, the group mask accepts a lot of different kinds of inputs. So I can just literally click this little button here. And let's say I want to spread from the bottom. I'm just going to grab, I think I need to be in points mode. Just grab this guy here. That's my start group. Now, if I preview falloff and animate, it's going to start spreading from here. And I'll change this to connectivity. So because this is a mesh, I'm going to get better results. So that looks like it's working. And then I can pipe this into anything. So let's do something that you should see is MOPs clip by attribute. This is a really simple little trick, but it's one that not a ton of people know about. What I can do with this case is basically pick a clip value and an attribute. And I can say any points that have a value of this attribute less than this value or greater than this value. So I can adjust this to sort of decide where I want to do the clip. Are going to be removed. And so if I animate the spread value, now you can see that this whole mesh is just really quickly being eroded. And you're getting smooth edges on this. It's not like just deleting by points. So you're not going to get like jittery individual primitives or points being blasted out. It's a smooth transition. And again, you can add noise to this. So you can get really specific about, maybe I want some high frequency noise in here and I want it to be less amplitude and like really break up that pattern and get spreads like this with no solvers. So you don't have to deal with a single SOP solver. It's real simple. It's entirely procedural. This is a lot of different ways that you can use this and any other falloff with the rest of MOPs. Yeah, you could create a group by border edges. So if you need to do it that way, you could turn on a point group, turn off the base, do include by edges, and then unshared edges. And now you'll get all of those points isolated. Okay, last thing for today. Sorry, it's taken a little bit extra time. I want to just go over a little bit about how falloffs can be used with SOPs that have nothing to do with MOPs. Because again, falloffs are just creating attributes, and there's something that you can use everywhere throughout Houdini where you can use a mask attribute. So really quickly, let's just try creating a box, and then I'm going to use a MOPs noise falloff. I need some more divisions on this box. I'm going to set it to be 16 by 16 by 16, so I get a few more in here. And then again, all of these, you don't have to use these with packed primitives. You don't have to use them with MOPs specifically. You can use this with whatever you want. And what I'm going to do is, let's just try, sure, simplex noise. I'm going to preview falloff. And instead of writing a MOPs falloff, I'm going to write to Z-scale because I can use it with the poly extrude. So let's promote this because when we're extruding, we're doing this per primitive. So we'll have to promote this like we would with any attribute. So I'm going to promote Z-scale from point to primitive and then drop down just a vanilla poly extrude SOP. And if you go to local control, there's a tag here for distance scale because you can vary this per primitive with the extrude operation. So if I enable this, the default attribute for this operation is Z-scale. Sorry, I think my display's gotten stuck again. Oh, you know what I need to do is I'm going to go into this noise falloff and then remap the output. So I'm going to set the maximum to be something much higher. And did I successfully promote this? Yes.
You didn't change the distance in the poly extrude.
Oh, yeah, duh. And I also need to change this to individual elements. There we go. Okay. Now I can bring this back down a bit. And so now, especially if I make this time varying, now I can get like this quick effect, and it can be used exactly the same as any other float attribute. So most artists who use MOPs get the most mileage out of falloffs because they're just really easy ways to create attributes that you can use to mask other effects, and you can use these with anything else in Houdini. So another really quick example, I can create a sphere here, and then I'm going to use Orient Mesh. The same way I did before, where I'm just going to create a default orientation on this. There's this handy thing in here called Visualize Up Vector that you can toggle on, and now I can actually see what direction up is facing. So right now it's a little bit wonky. Just turn off auto up, and now we've got this in a place that makes a little bit more sense. And let's do like a quick hair gen. Let's make this interesting. So I'm going to make these hairs on top of this. I'm going to turn the density way down because I don't want that many. So let's just do 100. And then I guess I could probably make them a little bit longer. Let's try, where is that option? Here we go. And then I can use shape falloff. And I mean, really, this can be whatever you want. It's not that important. I'll do a shape, like a sphere shape, and then maybe I'll change this radius to be a little bit bigger and then scale this down somewhat. But a lot of SOPs in Houdini accept mask attributes. So for example, guide process, when you're dealing with, let's do guide process bend. When you're dealing with hair, what I can do is take, when you're doing a bend operation, there's certain attributes that you can configure to basically make it look for attributes to use as masks. So if I set the attribute as bend here and I set the mode to be an axis skin attribute, this means that it's going to be looking for an attribute on the skin, which is like the sphere, the second input. So I can set this instead of axis skin attribute, I can set this axis to up. So now each of these things are going to curl along that up axis I defined. I can change this attribute to be something like, let's just do it at 180. And then the angle, similarly, I can use this with an axis. So where it says, sorry, where is that? Oh, okay. Angle, where it says this, I can go to guide attribute or skin attribute, whatever you want. I'm going to use guide attribute in this case. I'm going to set this to be MOPs falloff. And now what I can do is move this around, and it'll affect like locally which one of these things get bent. So again, any operation anywhere in Houdini, I'm just trying to drive that point home, can be affected by this because it's a float attribute. So anything that supports an input like this, you can use MOPs falloff with sort of wherever you want. let's just do one more quick thing here. The other situation where this really comes in handy is, let's say we've got like a simple pig head here. I'm going to scatter points on it. So just have this here and then do a quick noise fall off. And yeah, Deb, please stop me if I'm running out of time.
No, you're good.
Let's do simplex and preview it. Instead of time varying, maybe I'll just set this to be like negative time. So the noise is like moving up. So you can see it's kind of flowing up like a flame. Let's increase the frequency a little bit, make it a little bit more interesting. And then I'm going to remap it so that there's like less points active here. Maybe, I don't want that many. I want just a few sort of curling up at once. And then, another common thing that you can do a lot in Houdini is you can make ad hoc masks for groups. So if I want to, let's say, only keep certain points on here, I can say MOPs Falloff is less than 0.01 and set this to be a point group. And now I'm removing any points. It's hard to see, but I'm removing any points that aren't meeting that mask attribute. And so it's just like another quick way to generate easy random data or semi-random or even shaped data if you're using that kind of fall off. And now, just as a really quick example, I could, start using this to influence a particle simulation, right? So I could use a pop object and let's drop down a pop source. I'm just going to take those input points. So instead of scattering from the surface, I'm just going to emit from all points of the geometry wired into this thing. And I realize I'm going very fast, so I recommend taking a look at the example file if you want to just go step by step over each of these things. And then let's just get some wind in here. Let's have it moving slightly up, increase the air resistance so it's meeting the noise field, and then add a little bit of amplitude in here, and then pop solver really quick. And again, the point is that with all of this connected, what I can do is decide using simple shape operators, whether it's noise or shape fall off or whatever, to decide where I want these points to emit from, just by using them as an ad hoc mask. So anything that you can do with a point attribute in Houdini, you can use MOPs to kind of help you set those values a little bit easier or according to shapes that make more sense to you. So what this allows you to do is, for example, like right now, the spread fall off as it's spreading is very much like just directly from the bottom of this thing. But if I wanted to sort of lean the spread in one direction or another, I could actually use another fall off to do this if that's easier. So let's do like a shape fall off. And I'll have this one right to cost. And this is going this way, left to right, instead of down to up. What I can do in the spread fall off is basically say, consider this cost when you're determining the connectivity between things. So if I turn this on and then crank this scale, when I run the spread, it's still spreading sort of from top to bottom, but it's going to be really heavily slanted in that direction. So I can turn this down and now it's going to be a little bit more diagonal, but you can see that it's spreading upwards, but it really wants to start from the back to the front. So it's just a way of sort of nudging the spread in one direction or another, or trying to get it to evade certain channels until the closer to the end of the spread. You can add as many starting points as you want, so you can start the spread from multiple places and could animate it. But the one thing that I can't guarantee is that if you animate it, that you're going to get temporally consistent results from frame to frame. Because what's going to happen is, let's say you have point A, point B. When you run spread fall off, what it's doing before it does anything else is determining the relative distance of all of those points from those start points, and then mapping that to a 0 to 1 value. And then when you animate the spread, it's basically just clipping at those areas to figure out like where your spread function is going to land. And that's how it stays procedural. If you change that frame to frame, when it's doing that analysis, because polygons aren't perfect, when you're in connectivity mode, the connections that it draws between those things when it's sort of pathfinding could be different from frame to frame. And so you might get jitters when that happens. It's not really something that I can easily control against. You would probably get less jitters if you were operating in radius mode. rather than connectivity mode, but it's still expect to have to smooth things out after the fact, I would say. Yeah, if we have time, I can go over some basics of it. And I'm avoiding talking about MOPS Plus in this because I don't want to charge people for tutorials for software that I'm already charging for. MOPS has a YouTube channel that's also linked to FromMotionOperators.com that has a playlist of videos that are mostly tutorials, but there's also sort of an introductory video that sort of talks about what MOPS Plus is about and what it's meant to do. The wiki also, if you look at the node list, the wiki has both a sort of an overall tutorial on some parts of MOPS Plus, but also any node that you see on there that's marked plus is a plus only node that so it'll give you some sense of like what's actually included in the toolkit. And if you want to talk to me personally, like after these sessions, I'm absolutely happy to talk about it. I just didn't want to. I don't want to double dip. So this is a paid tutorial series for free software. Just trying to keep those things separate.